Artemis II isn't racing to the moon for flags or headlines. It's racing because Earth's protection is thinner than we like to believe. Step outside our magnetic cradle and the universe stops being scenery. It becomes a weapon. So what are we really trying to outrun? And what does this mission reveal about where humanity can survive next? There is a deadline written into the sky, and it is not set by politics, budgets, or pride. Artemis II moves now because the next great threat won't ask whether we are ready. In the wake of Apollo, we treated the moon like a finished chapter, an echo sealed in black and white. Yet the lunar surface is not merely scenery, it is a record of impacts, eruptions, and radiation written in stone. If you want to know what the solar system does to unshielded worlds, you study the scars that never healed. Artemis II returns to that record with a different purpose and a narrower margin for illusion. This mission is not an arrival so much as a calibration of distance, of time, of human attention, and of what fails first. Because beyond familiar orbits, safe stops being a place and becomes a process. The question behind the schedule is therefore stranger than it sounds. What is the real reason we are accelerating a human voyage to lunar distance again? The answer lives in the quiet intersection of competition and physics, of international rules and biological limits. It is found in how a spacecraft becomes a habitat, and how a habitat becomes a promise. We will follow the crew, chosen for competence under uncertainty, as they train for a flight that offers no casual exits. We will step inside Orion as if it were a living system, where every valve and line of code is a vote for survival. And we will watch the space launch system turn minutes into miles, until Earth is no longer a horizon, but a shrinking signal. Along the way, setbacks will not read like footnotes, they will become the drama. Heat will behave like an adversary with a memory, air will become a budget, and re-entry will demand an answer that cannot be negotiated. Each delay, each redesign, each test is a reminder that nature does not grade on effort. Then comes the arc that makes this mission more than a rehearsal, an outward loop that carries humans farther than Apollo into a geometry where rescue is not a plan. There will be a moment when the moon is between the crew and every antenna on Earth. In that silence, the mission stops being a headline and becomes a verdict. What returns from that passage is not just a capsule and 4 heartbeats, it is evidence about what kind of transportation chain can be repeated, what standards must be shared, and what cislunar space will demand from anyone who intends to stay. And beneath the engineering, a deeper implication begins to form. The moon is both the nearest archive of cosmic violence and the nearest construction site for a future that does not end at one planet. This documentary follows Artemis II as a race against ignorance, not nostalgia. We are going to trace the pressures that compress timelines, the design choices that turn risk into method, and the emerging architecture that could make the space between worlds a place where humans can operate, reliably, repeatedly, and without myth. Because the moon is close enough to reach and far enough to reveal what we truly are. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin with the new moon race and the rules it is quietly setting. Then move through the people, the ship, the crises, and the flight itself. And when Earth disappears behind the moon, we'll see what this loop enables next and why the pace is tightening. Artemis II is described as a return to the moon, but it behaves like a departure. It leaves the familiar economy of low Earth orbit and tests the first link in a chain. That chain is meant to hold people in deep space long enough to stay and to come back with systems intact. The question is, why now? And why this kind of mission? If it were only about flags and firsts, the schedule would be simpler. Artemis II is racing because the environment beyond Earth is not patient, and because engineering calendars rarely forgive hesitation. It is also racing because politics, rules, and supply lines harden quickly once a route becomes normal. Apollo was a sprint for prestige, executed under a single national imperative. It optimized for speed, television, and a decisive landing before rivals could claim the same image. Even the hardware reflected that urgency. Thin margins, narrow windows, and a willingness to accept risk. Artemis is a systems program that assumes repetition, maintenance, and replacement. Because it expects the moon to be visited like a port, it is designed to support sustained lunar presence and eventually stage toward Mars. That means thinking in terms of lifetimes, not headlines, and in terms of spare parts, not singular triumphs. It also means designing for crews who will inherit procedures written by earlier crews, then revise them under pressure. That shift changes what counts as success. A single footprint proves capability, but it does not create resilience. A durable cislunar architecture requires power, navigation, docking, communications, and logistics, all functioning as a network rather than a stunt. It requires crews who can leave, return, and leave again, without treating each flight as an exception. This chapter reframes Artemis II as the pivot point between symbolic exploration and infrastructure. It is not the landing mission, and that is the point, because the program needs a human-rated transportation layer before it needs a flag. It is the crude stress test of Orion, life support, operations, and recovery, under conditions that cannot be simulated perfectly on Earth. It is also a statement about how to survive the unknown, by building margins that are boring until they are life-saving. To understand the urgency, we have to change our map of space. Low Earth orbit feels like space, but it is still inside Earth's protective influence, where radio contact is steady and rescue is at least imaginable. It sits within the magnetosphere, a moving shield shaped by solar wind, with a long tail that streams away from the sun. It is a bubble where many hazards are reduced, not removed, and where the planet quietly does much of the work. Inside that bubble, radiation is filtered and trapped in complex belts. The Van Allen belts hold charged particles in looping paths along magnetic field lines, creating regions that satellites learn to avoid or traverse quickly. Astronauts in low orbit still receive radiation, but the dose is moderated by Earth's field and by the thin blanket of atmosphere below. Outside it, the rules change, and exposure becomes continuous, like stepping out from under a roof into open weather. Galactic cosmic rays arrive from distant explosions and accelerated particles, moving so fast that shielding becomes a trade between mass and secondary radiation. These ions are not just energetic, they are heavy, and they can slice through tissue at the cellular level. Solar particle events can surge without warning, turning hours into a medical emergency if a crew lacks shelter or time. Space weather is not metaphorical out there. It is a physical forecast written in protons. Micrometeoroids add another layer of risk. In deep space, impacts are not rare anomalies, but background conditions, like invisible grit in a constant stream. Tiny grains carry enormous kinetic energy at orbital speeds because velocity multiplies damage more than size suggests. A paint fleck can punch like a bullet, and a grain of sand can behave like shrapnel. Over long durations, the difference between nuisance and catastrophe becomes a matter of shielding, geometry, and luck. These are not abstract threats, and they are not new. They are the same forces that shaped planetary surfaces and atmospheres long before human schedules existed. Radiation alters chemistry, damages DNA, and drives evolutionary pressure, which is why life on Earth evolved under protection and repair. Impacts rewrite geology and sometimes reset biological history, leaving thin layers in rock that mark sudden endings. When we talk about deep space risk, we are really talking about the baseline physics of the solar system. Leaving low Earth orbit means entering a realm with a long memory. The Moon preserves that memory in its craters and regolith because it has no weather to soften edges and no oceans to recycle scars. Its surface is powdered glass and shattered stone, churned by billions of years of impacts into a fine, clinging dust. Earth erases most of its own record through weather, plate tectonics, and oceans, which makes our planet feel timeless. Artemis II is a human mission, but it is also a cosmology lesson written in terrain. So why send a crew now, before the bases and depots exist? Because you cannot build an off-world system without proving the human link, and because humans change the definition of failure. Robots can map and scout, but crews reveal failure modes that simulations miss, especially when fatigue and improvisation enter the loop. Deep space punishes small oversights with compounding consequences, because there is no nearby warehouse and no quick tow back to port. Artemis II's trajectory is built around that reality. It uses a free return path that loops around the moon and comes home, allowing gravity to do the steering that fuel would otherwise provide. The shape is often described as a figure 8 in space, but the feeling is more like a slingshot that never lets go. The moon's gravity bends Orion's path and throws it back toward Earth, turning a distant flyby into a disciplined rehearsal. The key feature is that it works with minimal propulsion. If engines fail at the wrong time, the spacecraft still has a route home, because the geometry of the orbit is designed to intersect Earth again. It is not a guarantee of safety, but it is a designed margin, and margins are what separate exploration from gambling. It is an operational philosophy built into the flight plan, where the safest option is not an afterthought. Apollo 13 made the free return trajectory famous through crisis. The crew did not choose it for elegance, they used it because it was the only stable path left after an explosion redefined their mission. Artemis II chooses it intentionally, before the crisis exists, and that difference matters. That choice signals what this mission is really testing, and what it refuses to romanticize. It is testing whether deep space can be approached with layered safety, not bravado, and whether discipline can be made routine. The free return also frames the mission as a boundary crossing. Orion will travel farther than any crewed spacecraft in decades, moving beyond the familiar ring of satellites into a darker, emptier volume. The plan is to exceed Apollo 13's farthest human distance of 252,760 miles, a number that still carries the weight of a near disaster. That number becomes a line between eras, not because miles matter, but because exposure does. Past a certain distance, Earth stops feeling like a nearby home and starts feeling like an object. Distance is narrative tension, but it is also engineering reality. Communications delays grow, and even a few seconds can change how crews talk, how controllers listen, and how decisions are made. Rescue becomes impossible in any practical sense, which forces self-reliance to become a system requirement rather than a slogan. Radiation dose accumulates, and shielding becomes a design argument, because every kilogram must justify itself. The farther you go, the more you must carry your own world with you. Air, water, heat, and the ability to fix what breaks. Artemis II therefore becomes a rehearsal for permanence. It is not yet settlement, but it is rule-making in hardware, where every valve and display implies a future routine. Every procedure, checklist, and recovery operation becomes a template, and templates quietly outlive the people who write them. Templates become standards, and standards become infrastructure, because the next mission will inherit what this one proves. Even the mundane moments, sleep cycles, waste handling, carbon dioxide scrubbing, become evidence that humans can function beyond the bubble. That brings us to the second race, which is not a mirror of the first. The new race is multipolar and institutional, not binary and cinematic, and it unfolds through memoranda as much as rockets. China has a clear lunar timeline and a growing launch cadence, which signals intent through repetition rather than spectacle. Its partners are building an alternative framework through the ILRS concept, offering a different set of technical interfaces and diplomatic expectations. In the background, every successful mission makes the next one easier because experience compounds. In this landscape, the moon is not just a destination, it is a place where norms will be established by whoever shows up, operates reliably, and shares access without chaos. The question becomes, who defines safe behavior, resource use, and coordination, especially when multiple actors want the same regions? In cislunar space, rules precede settlement because conflict is easier than repair, and because misunderstandings can become policy. What does responsible mean when the nearest courtroom is 250,000 miles away? The Artemis Accords are one attempt to set those norms early. They emphasize transparency, interoperability, and peaceful purposes, which sounds abstract until hardware has to dock, share data, or avoid interference. They also address resource extraction and safety zones as practical necessities, because mining or processing requires predictable boundaries for operations. Critics see power projection, and supporters see a way to prevent ambiguity from becoming confrontation. Either way, the language is a preview of how the moon may be governed, by precedent, not by perfect consensus. The coalition aspect is central to why Artemis feels like a race. Over 60 nations have signed the accords, creating a diplomatic perimeter around future activity and making participation feel like a choice with deadlines. Partnerships with companies shift timelines and incentives because industry moves when contracts turn risk into revenue. Public-private contracts turn exploration into supply chains, and supply chains demand predictability, from launch cadence to standards for docking rings. When supply chains appear, exploration stops being a one-off story and becomes an economic habit. This is a different kind of momentum than Apollo had. Apollo could end when the political goal was met, because the architecture was not built to be maintained indefinitely. Artemis cannot end cleanly if it becomes an ecosystem of partners, because shared investments create shared dependencies. Once multiple actors invest, stopping becomes a strategic decision with costs, not a simple budget line. The program's continuity becomes part of its message, even when the message is never spoken aloud. Artemis II sits at the hinge between aspiration and governance. It is a crewed mission that validates a transportation layer, and transportation layers decide who can participate and at what price. Price shapes frequency, and frequency shapes permanence, because routine is what turns a frontier into a corridor. If Orion and its operations can be repeated, then the moon becomes less like an expedition and more like a destination with schedules. Yet the program still needs public meaning, not just logistics. That is why symbolic payloads ride alongside sensors and procedures, sharing the same capsule and the same risk. Orion carries an archive of 5.6 million names, a mass signature of collective presence, as if the mission is carrying a crowd in miniature. It carries a piece of Wright Flyer fabric, linking first flight to deep space, and reminding us that fragile beginnings can scale into infrastructure. It carries moon tree soil, a reminder that exploration returns to Earth as biology and memory, not only as data. It carries an art piece titled Rise, designed as a deliberate echo of Earthrise. These objects are narrative glue, but they also reveal intention, because they are chosen with care rather than convenience. The mission wants a renewed planetary perspective at the moment it leaves the cradle, when Earth is no longer a horizon, but a sphere. In the window, the planet will shrink into a bright coin, and the black around it will look less like emptiness and more like exposure. Earthrise worked because it made Earth look small and shared, and because it arrived during an era when images could change politics. Rise aims to update that effect for a new era of division and acceleration, where attention is fragmented and urgency is constant. The message is not that space is beautiful, but that Earth is singular and that its boundaries are thin. The subtext is that we may need that unity to survive what comes next, because deep space does not care about our arguments. Artemis II, therefore, operates on two levels at once. It is a technical mission to prove deep space operations with a safety-first trajectory, where the free return path embodies a philosophy of restraint. It is also a geopolitical move to anchor norms and partnerships before alternatives dominate, because early standards become default standards. And it is a cosmological reminder that outside the magnetosphere, nature is indifferent, and indifference is its own kind of pressure. The central question returns with sharper edges. Is Artemis II racing for glory or racing to build a foothold before the hazards and politics converge. If the universe is a hostile medium, then infrastructure is the real exploration, because it is what makes hostility survivable. The Moon becomes the first test site for living beyond Earth's protection, where every success is measured in repeatability. What does it mean to call something home, when home must be assembled, checked, and maintained? From here, we move from framing to mechanics. We follow Orion out of the bubble and into the radiation weather, where the numbers on dosimeters become part of the story. We examine what must work, what can fail, and what this mission quietly commits us to becoming, an interplanetary species that survives by planning for the ordinary. Artemis II is a flight test, but it is also a human experiment conducted inside a sealed machine. Chapter 1 left the magnetosphere and named the hazards, from radiation to micrometeoroids. Chapter 2 asks what kind of people can function there when the universe offers no sympathy and no second chances. The crew is 4 specialists, but the mission treats them as one organism with shared senses. Reed Wiseman commands the vehicle and the tempo of decisions, where timing can be as critical as thrust. Victor Glover flies the profile and guards the margins, because margins are what keep options alive. Christina Cook owns systems thinking, where small anomalies become early warnings rather than late surprises. Jeremy Hansen carries a national first, and the pressure of representing a partner beyond low Earth orbit. Their stakes are not abstract, because trans-lunar injection is a one-way commitment in practice and psychology. Once Orion lights that burn, the quick return fantasy ends, and the timeline becomes stubborn. The Moon is not far in distance alone. It is far in consequence and in communications geometry. A mistake can become a multi-day problem before Earth can do anything meaningful. In mission design, trans-lunar injection is a precise energy change, a burn that targets a narrow corridor. In human terms, it is a door closing behind you, quietly, without drama and without reversal. Even if the trajectory is planned for free return, the spacecraft must remain healthy enough to ride it. The crew must think in hours and days, not in minutes and rescue helicopters. They call themselves integrity, and the word becomes a design requirement rather than a slogan. Integrity means telling the truth early, before pride turns it into a crisis that spreads. Integrity means admitting uncertainty, because deep space punishes overconfidence with compounding errors. Integrity means trusting crewmates enough to be corrected in real time, without treating correction as insult. The call sign also echoes an older tradition, when crews named themselves to set a tone. Apollo crews carried names that became shorthand for their style and sometimes for their fate. In Artemis, the name is chosen with full awareness of what the Moon did to earlier hardware. Integrity is an answer to that history, an insistence that honesty is a life support system. Human factors are treated like mission-critical hardware, not soft culture or motivational talk. Fatigue changes perception, and perception changes flight control inputs in small, cumulative ways. Stress narrows attention, and narrow attention misses cascading failures that begin as minor. In deep space, psychology becomes engineering, because cognition is part of the control loop. That control loop is literal, not metaphorical, because humans interpret displays and then command actuators. A tired brain reads a number, delays a response, and a valve stays open too long. A distracted mind hears a call-out, misfiles it, and a checklist step is skipped. The spacecraft does not know why the error happened. It only lives with the consequences. Training starts with roles, but it quickly becomes cross-competence and shared vocabulary. Wiseman must understand life support, because command decisions touch oxygen, power, and thermal margins. Glover must read guidance and navigation, but also recognize when sensors lie or saturate. Koch must know every subsystem, then teach it back under pressure when time is scarce. Hansen must integrate into NASA procedures, while also translating them into coalition expectations. Cross-competence is not about turning everyone into the same person, because specialization still matters. It is about building redundancy that can think, because hardware redundancy can only switch states. When one crew member is overloaded, another must notice and intervene before performance slips. That intervention must be welcomed, because deep space does not tolerate ego-driven silence. This is the first transition from Chapter 1's environment to Chapter 2's people. The hazards outside Earth's shield are constant, so the crew must become constant too. They cannot negotiate with radiation or vacuum, so they negotiate with themselves. They build habits that hold when novelty fades and when fatigue becomes ordinary. The mission profile looks conservative, but it is cognitively demanding in ways that do not show up on posters. Orion will arc toward the moon, then swing behind it into radio silence. The crew will lose real-time contact, and the silence will feel like a physical wall closing in. Autonomy is not a slogan in that moment. It is the only operating mode. Behind the moon, Earth becomes a blocked line of sight, and the radio link collapses by geometry alone. The cabin is still full of voices, fans, and alarms, yet the outside world goes mute. That contrast can be unsettling, an ancient human reaction to isolation in unfamiliar terrain. Artemis II trains to make that reaction visible, so it can be managed rather than denied. Even with a free return trajectory, there is no instant rescue and no rapid replacement parts. Controllers can advise, but they cannot turn wrenches or smell smoke in the cabin. A medical emergency cannot be evacuated in hours, only managed in place with limited supplies. A systems failure cannot be swapped with spares from a nearby station because there is no nearby station. So Artemis II trains for the uncomfortable truth that the crew is the mission's final layer. They are the maintenance team, the science team, and the emergency response team at once. They must diagnose faults while also protecting their own bodies from stress and exposure. They must keep the spacecraft alive while also keeping their judgment intact. The program treats training as a rehearsal for distance itself, not merely for a timeline. It is not enough to memorize checklists because failures rarely match the script. The crew must understand why a procedure exists and when it must be adapted safely. Deep systems knowledge becomes the only reliable tool when the unexpected arrives. That knowledge includes the logic of sensors, because sensors are both eyes and potential liars. A pressure transducer can drift, a temperature probe can lag, and a software filter can smooth away a real spike. In a crisis, a single bad number can pull attention toward the wrong subsystem. The crew learns to ask what a measurement truly represents and what it might be missing. That is why Artemis II turns pilots into field scientists and scientists into disciplined operators. The mission is a flyby, but it is not a joyride framed by windows. Humans are carried to the moon because humans can notice what instruments miss. A trained eye can integrate context, lighting, and texture in seconds, then translate it into operational language. Human vision is not just resolution, it is interpretation under changing illumination. The eye and brain amplify edges, search for patterns, and sometimes invent certainty where there is none. In spaceflight, that tendency can be dangerous, because a confident misread can drive a confident mistake. Training does not remove bias, but it teaches crews to label it and compensate. Near the Terminator, the moon becomes a test of perception and restraint. Low sun angles stretch shadows and exaggerate relief, making small ridges look like cliffs. Subtle albedo changes can signal composition differences, or simply geometry and viewing angle. The crew must learn to separate illusion from information, and to do it quickly. Visually, the Terminator is a knife edge, where night and day meet in slow motion. Crater rims glow like thin crescents, and the floors drop into ink-black cold. Mountains cast shadows that feel too long to be real, because there is no air to soften them. The scene is beautiful, but the lesson is practical. Contrast can mislead. They practice describing what they see with disciplined language, because language is a tool for shared reality. They learn to call out brightness, grain, and boundary sharpness without guessing at causes. They learn to compare features across time as lighting shifts, so change does not become confusion. They learn to report like sensors, not like tourists. That discipline includes admitting what cannot be known from a single glance. A feature may look like a boulder field, yet be a shadowed slope with scattered blocks. A bright patch may suggest fresh material, yet be a highland exposure catching sunlight. The crew is trained to say, uncertain, without embarrassment, because uncertainty is safer than false precision. Geology training is not a side quest. It is mission readiness tied to future landings. The moon's surface is a record of impacts and volcanism preserved without weather's erasing hand. If humans are going to build there, they must read that record quickly and reliably. If humans are going to study origins, they must connect observations to theory under time pressure. At the Lunar Sample Laboratory, the crew handles the moon's vocabulary with gloved hands and careful posture. They learn anorthosite, the pale crustal rock tied to a magma ocean and early differentiation. They learn basalts, the dark mare lavas that filled ancient basins after the violence. They learn breccias, the welded chaos of impacts that mixed everything together. The lab itself is part museum, part cleanroom, and part time machine. Under bright lights, samples sit behind glass and nitrogen purge systems protected from Earth's moisture. A small chip of rock can hold billions of years of history in its minerals. The crew learns to treat that history with respect, because contamination is irreversible. They learn that each sample is a timestamp of violence, written in fractures and melted edges. Breccias preserve shock and heat from collisions that reshaped the early solar system's architecture. Basalts mark internal heat and volcanic plumbing, long after the biggest impacts faded. Anorthosites point to a young moon that once behaved like a molten world. Scientific details become operational context because future crews will rely on these interpretations. Anorthosite suggests plagioclase floated in a global magma ocean, forming a buoyant crust as heavier minerals sank. Basalt suggests mantle melting and lava transport through fractures, filling basins like dark ink. Breccia suggests repeated impacts, where older rocks are shattered, mixed, and re-cemented. The giant impact hypothesis is not taught as trivia, but as context for everything the crew will see. A Mars-sized body collides with early Earth, and debris becomes the moon in a hot, chaotic disk. That event changes Earth's spin, tides, and long-term stability, leaving fingerprints in angular momentum. It may also help explain why Earth stayed habitable while other worlds diverged. Historically, this idea matured as scientists compared lunar samples with Earth rocks and meteorites. The moon is depleted in volatiles, suggesting high temperatures and loss of light elements during formation. Isotopic similarities to Earth hint at shared material, yet differences in iron content imply separation. The theory is still refined, but it remains the best framework for the evidence. The crew is trained to connect that origin story to what the moon looks like today in stark sunlight. The battered surface is not random damage. It is a preserved archive of early solar system dynamics. The crater density is a measure of time and a measure of bombardment intensity. The regolith is a gardened layer of shattered rock built by constant micrometeoroid churn. Regolith is not soil in the Earth sense because it has no biology and no water chemistry. It is angular, abrasive, and electrostatically active, clinging to surfaces in vacuum. It records solar wind implantation, embedding hydrogen and helium in grains over eons. It also records cosmic ray exposure, which can alter crystal lattices and create new isotopes. Training then leaves the lab and goes to analog landscapes, where the body learns what the mind cannot. The point is not to pretend Earth is the moon, because Earth is too alive and too wet. The point is to practice decision-making in terrain that forces attention and disciplined communication. The crew learns to observe, move, and speak under constraints. Mistasting Crater in Labrador becomes a classroom for impact physics and for humility. It is a scar made by energy, not by erosion, and it still reads as violence. The crew sees melt rocks that formed in seconds, then cooled into new textures like frozen turbulence. They learn shock metamorphism, where minerals record pressures beyond normal geology. In the field, the visuals are blunt and instructive. Broken rock faces show glassy veins, and shattered blocks lie where they were thrown long ago. A lake fills the crater now, reflecting clouds that the moon never had. That contrast, Earth's softness overlaying an impact's hard geometry, makes the moon's preservation feel even more severe. They learn how impacts excavate deep layers and spread them outward in radial patterns. They learn how central uplifts form when rock rebounds like fluid, briefly losing its strength under extreme stress. They learn how ejector blankets can hide older surfaces, then become surfaces themselves over time. They learn why the moon's craters are not just holes, but structural reorganizations. Impact physics also carries a lesson about speed, because velocity is the hidden multiplier. A small object at tens of kilometers per second releases energy like an explosion, compressing rock beyond its elastic limit. Shock waves propagate, reflect, and interfere, creating complex fracture networks. The crew does not need to compute the equations, but they must respect the scale. Mistasting also teaches repetition and statistical thinking, because one crater is never the full story. On Earth, weather and tectonics erase most impact evidence, making craters rare and often subtle. On the Moon, impacts remain, layered like pages that cannot be turned back. The crew learns that lunar history is written by collisions, and that collisions are the solar system's baseline behavior. That baseline behavior invites an uncomfortable question, one Artemis training does not avoid. If impacts are normal, then safety is the exception that must be engineered. Earth feels stable because it is buffered by air, magnetic fields, and active geology. The Moon feels stable because it is dead, and dead surfaces keep their scars. Iceland then shifts the lesson from impacts to volcanism, and from scars to flows. Basaltic deserts resemble the mare in composition and color, especially under flat, grey light. Lava fields teach navigation across rough, fractured ground, where a misstep can twist an ankle. The crew practices describing flow textures, vesicles, and layering with consistent terms. The Icelandic landscape offers visuals that echo lunar imagery without pretending to be lunar. Black rock spreads in rippled sheets, and old flows stack like pages of cooled liquid. Steam vents and moss remind you that Earth is active, yet the basalt underfoot feels ancient. The crew learns to separate the analogy from the reality, while still extracting useful practice. Iceland is also used to simulate polar lighting problems, where the sun skims the horizon. Low sun angles create long shadows and ambiguous slopes, making depth cues unreliable. Features look steeper than they are, and flat ground can hide hazards in darkness. The crew learns to move and judge distance when contrast lies. This matters because Artemis is chasing the lunar South Pole, a region defined by geometry. The pole is a place of extreme illumination and persistent shadow, where some ridges see near-continuous sunlight. Nearby craters can remain dark for billions of years, acting as cold traps. It is where water ice may survive, locked in temperatures so low that molecules barely move. The South Pole is also where human vision can be fooled, and where robotics can be confused by glare. Bright, sunlit slopes can saturate cameras, while adjacent shadows swallow detail. A safe route can look dangerous, and a dangerous slope can look flat. Artemis II will not land, but it trains the eyes and language that future landings will depend on. Artemis II will not land, but it will set the cognitive standard for what comes next. It will test how crews talk about terrain under difficult lighting without slipping into guesswork. It will test how quickly humans can build a shared mental map from partial views. It will test whether trained observation can become operationally useful, not just scientifically interesting. The training pipeline then pivots to isolation and autonomy, because isolation is a force multiplier. The crew practices being cut off from immediate help, even while surrounded by instructors and safety nets. They run timelines where communications are delayed or interrupted, and where guidance arrives too late. They learn to make decisions with incomplete data, then live with the consequences. In these runs, the cabin becomes its own small world, with its own weather of emotion. A minor glitch can trigger a rush of adrenaline, and adrenaline can distort time perception. The crew learns to slow their breathing, slow their speech, and slow their hands. They learn that calm is not personality, it is a practiced technique. This is where integrity becomes more than a call sign and more than an aspiration. Candor is trained as a habit because hidden mistakes compound in closed systems. Humility is trained as a reflex because the spacecraft does not care who is right. Trust is trained as a procedure because teamwork is the only redundancy that thinks. Trust has a technical dimension because it determines how information moves. If a crew member hesitates to report confusion, the team loses time and loses options. If someone hides fatigue, the team misjudges risk and workload distribution. Integrity means making the invisible visible before it becomes a failure mode. They also train for the body's limits, because deep space is not neutral to physiology. Microgravity shifts fluids toward the head and changes vision over time, sometimes altering the shape of the eye. Muscles and bones decondition without constant countermeasures, even on short missions. Sleep becomes fragile when schedules, noise, and stress collide. Appetite and mood become variables that can degrade performance, especially when novelty fades. A crew that eats poorly becomes a crew that thinks poorly, because glucose and hydration affect cognition. Small irritations can grow in confined volume, where privacy is limited and routines repeat. Training includes learning each other's cues, so a change is noticed early. Radiation is treated as an invisible operational constraint, not a distant theoretical hazard. Dosimeters become part of the daily rhythm, and readings are discussed like fuel and power. The crew learns what a rising dose means and what actions reduce risk in practical terms. They learn that shielding is partial, and that time is sometimes the only defense. Radiation in deep space includes galactic cosmic rays and solar particle events, each with different character. Cosmic rays are a steady drizzle of high-energy particles that can penetrate materials and damage DNA. Solar events can arrive as storms, with protons that spike dose quickly. Orion's design and procedures aim to reduce exposure, but they cannot make it disappear. Emergency simulations are built around the failures that matter most, because consequences are amplified by distance. Fire is the nightmare in a sealed cabin, because smoke has nowhere to go and heat can spread. Depressurization is a race against hypoxia, because consciousness can vanish quickly. Toxic atmosphere events are insidious, because symptoms can mimic fatigue until it is too late. Beyond Earth's rapid return envelope, these events change character and become endurance problems. In low Earth orbit, a vehicle can deorbit within hours, and rescue assets can converge quickly. In cislunar space, the timeline stretches into days, and the crew must remain functional. Stabilizing the situation is only phase 1, because then they must keep living with the damage. They train to isolate modules, close hatches, and manage pressure loss with practiced choreography. They train to don masks and identify contaminants by sensor and smell, while keeping communication clear. They train to fight a fire without creating a worse one, because extinguishers can stir debris. They train to conserve consumables while also keeping clarity because panic wastes resources. Life support failures are treated as slow-motion emergencies, where the clock is measured in chemistry. ECLSS is not one system, it is a chain of interdependent loops that can fail subtly. Carbon dioxide removal protects cognition before it protects comfort, because CO2 impairs thinking early. Water processing protects mass budgets before it protects convenience, because water is heavy and finite. In training, the crew learns to recognize the early signatures of ECLSS trouble. A slight rise in humidity can hint at a condenser issue, and a smell can hint at off-gassing. A sensor alarm might be real, or it might be a drift that masks a deeper problem. The crew practices confirming, isolating, and responding without rushing into the wrong fix. Power faults are trained as cascading puzzles because electricity is the bloodstream of the spacecraft. A battery issue can become a thermal issue, then an avionics issue when heaters shut down. A sensor dropout can become a navigation uncertainty, then a propellant waste as corrections grow. The crew learns to think in dependencies, not in isolated boxes. Thermal control is part of that dependency chain because space is unforgiving about heat. In vacuum, heat does not convect away, so radiators and loops must do the work. Too cold and systems stiffen, too hot and electronics drift or fail. The crew trains to read thermal trends like weather forecasts because trends matter more than snapshots. Avionics anomalies are trained as ambiguity, not as clean alarms with clear causes. A false reading can trigger the wrong response and create real damage, especially when automation is trusted blindly. The crew learns to cross-check instruments and trust patterns, not single numbers. They learn to slow down when the display demands speed, because urgency can be a trap. Every simulation is built to force a choice under time pressure, because choice reveals character. The instructors want to see how the crew argues, not just what they decide in the end. They want to see whether disagreement stays productive, with evidence and clear language. They want to see whether integrity survives stress, when tone and posture begin to slip. Sometimes the lesson is not technical, but interpersonal and immediate. One person may fixate on a solution, while another sees a broader risk. The crew practices interrupting that fixation without escalating conflict. They learn to ask, "What are we missing?" A simple question that can reopen perception. The tension is that the moon does not offer a pause button, and the timeline keeps advancing. Translunar injection commits the crew to a corridor where options narrow as propellant, power, and time are spent. The free return path is a safety net, but it is still a path with constraints. The crew must keep Orion healthy long enough to ride it home. This is the second transition, from training details to cosmology. The crew is not only preparing for distance, they are preparing for the conditions that made the moon what it is. The same physics that threatens them also wrote the landscape they will study. In that sense, the mission is both survival and interpretation. The moon's battered face is a map of indifference, carved without intention or malice. Impacts did not aim, they simply happened, following gravity and probability. Radiation did not negotiate, it simply arrived, particle by particle, year by year. The same forces that carved craters also shaped Earth's biological opportunities by filtering what reached the surface. Earth's habitability is partly a story of shielding and recycling, and partly a story of luck. Our atmosphere burns up small debris and softens radiation's edge, turning lethal flux into manageable background. Plate tectonics erases scars and renews chemistry, cycling carbon and water through deep time. The magnetosphere deflects charged particles and reduces chronic exposure, though it cannot stop everything. The moon lacks those protections, which is why it preserves history with brutal clarity. Its surface is a museum of impacts, solar wind implantation, and cosmic ray gardening that never rests. That museum is also a warning, because it shows what the solar system does by default. It shows what Earth avoids and what Earth cannot always avoid. When you look at the moon through this lens, craters become more than scenery. They become statistics made visible, a record of how often space throws rocks at worlds. The regolith becomes more than dust, becoming a ledger of radiation exposure and micrometeoroid strikes. The silence becomes more than poetic, becoming the absence of buffering processes. Artemis II, therefore, becomes a bridge between human training and planetary truth, linking procedure to geology. The crew learns geology to read the archive, and emergency response to survive the archive. They learn to interpret shadows because the poles hide resources and hazards in the same frame. They learn to manage systems because the spacecraft is their only atmosphere. They also learn that exploration is not a heroic mood, it is a discipline that must be repeatable. The universe will not reward courage with safety because physics does not recognize bravery. It will only reward preparation with a chance, and even that chance is conditional. Integrity is the name for that preparation when it is shared, spoken, and enforced. The final phase of training returns to Earth, because returning is part of the test and part of the proof. Recovery training with the Navy and DoD rehearses the last choreography, where minutes matter again. The capsule hits the ocean, and teams move with practiced precision across waves and wind. The crew must be extracted safely, even if they are injured or disoriented. Visually, recovery is a contrast to deep space's silence, because it is loud and crowded. Helicopter rotors beat the air, boats cut white wakes, and divers reach the capsule's heat-scarred skin. The ocean heaves, indifferent in its own way, yet familiar compared to vacuum. The crew emerges into daylight, blinking, carrying the mission in their posture. Splashdown is framed as the end of a cosmic loop, and the loop has meaning beyond ceremony. The mission leaves Earth's cradle, crosses into harsher physics, then comes back carrying proof. Proof is not a speech. It is a functioning crew and a functioning spacecraft. Proof is that humans can cross the space between worlds, then rejoin the planet intact. Artemis II is racing because the gap between worlds is the real obstacle, not just the distance. The crew, called Integrity, is the program's answer to that gap, built from training and from deliberate culture. They train to become reliable under indifference, because indifference is the true environment. In the next chapter, the spacecraft itself must prove it can match them. Chapter 1 named the environment beyond Earth's shield. Chapter 2 trained humans to endure it. Chapter 3 turns to the machine that must keep them alive when distance becomes irreversible. Leaving low Earth orbit is not just a navigation change or a new line on a flight plan. It is a boundary crossing from buffered space into a radiation and micrometeoroid regime that never stops. In low orbit, Earth's magnetic field bends charged particles away, and the atmosphere still skims the spacecraft's path. Beyond that cocoon, the background becomes more honest. Solar particles, galactic cosmic rays, and dust moving at orbital speeds. Visually, the transition is subtle at first. The blue limb fades thinner, the city lights fall away, and the planet becomes a single object rather than a world of places. Yet the physics changes immediately, because shielding by proximity is no longer guaranteed. The spacecraft becomes the crew's only local environment, a small engineered bubble moving through a large indifferent volume. The first barrier is energy, and it is not metaphorical. Earth's gravity well is a deep pit, and every kilogram of shelter must be lifted out before it can protect anyone. The rocket equation sits behind every design decision, quietly punishing extra mass with exponential propellant demand. Even a few millimeters of shielding, multiplied across a capsule, becomes a serious cost in fuel and thrust. That cost is why launch vehicles look brutal rather than elegant. They are machines that trade chemical bonds for altitude and velocity, and they must do it quickly. In the first minutes, the atmosphere is thick enough to tear structures apart, and gravity is strong enough to steal energy continuously. The vehicle has to win both arguments at once. SLS Block 1 is built around that brute requirement, and it wears its purpose openly. It is less a rocket than a controlled release of stored chemical potential aimed at a narrow corridor. The corridor is not just a direction in space, it is a timed sequence of pressures, temperatures, and accelerations that must remain inside narrow limits. On the pad, the stack is motionless but already alive. Venting vapor curls off the core stage, and frost blooms on metal that is being held far below ambient temperature. The vehicle looks like it is breathing, because cryogenic propellants are always trying to boil. The ground systems exist to keep that boiling from becoming instability. The core stage is a cryogenic machine that lives on the edge of phase change. Liquid hydrogen is stored near 20 Kelvin and liquid oxygen near 90 Kelvin. Temperatures so low they reshape material behavior. Metals contract, seals stiffen, and any stray heat leak becomes a measurable loss. The tanks are enormous because hydrogen is light, and volume is the price paid for high specific impulse. Inside the core stage, plumbing and valves must handle propellants that can flash into gas if pressures drift. Sensors watch temperatures and flow rates with obsessive attention, because small anomalies can cascade into engine instability. The stage's insulation and structural design are therefore not cosmetic. They are part of the propulsion system because they keep the propellants in the state the engines require. 4 RS-25 engines sit at the base like a cluster of proven hearts, each one with its own history. They are high-performance, staged combustion engines that turn cryogens into acceleration. In staged combustion, propellants are partially burned in a pre-burner to drive turbopumps, then fed into the main chamber for full combustion. The result is efficiency, but also complexity that must be mastered. The turbopumps in an RS-25 spin at extraordinary speeds, forcing propellant through the engine with precision. Hydrogen, in particular, is difficult because it is small, cold, and prone to leakage. The engine must keep combustion stable while the vehicle shakes, bends, and climbs through changing atmospheric conditions. That is why the RS-25 is not merely powerful, it is controlled power, throttled and managed rather than simply unleashed. Their heritage matters because first crewed deep space flights cannot afford novelty everywhere. A known engine reduces unknown failure modes when the mission's stakes are human. The RS-25 lineage carries test data, operational experience, and a long record of post-flight inspection. That record becomes a form of shielding against uncertainty, the kind no physical material can provide. Historically, this is one of the quiet lessons of human spaceflight. Programs that survived did not survive by being new in every subsystem. They survived by choosing where to innovate and where to rely on demonstrated behavior. Artemis inherits that philosophy because distance makes rescue and improvisation less plausible. But the RS-25s are only part of the story and not the loudest part. The 5-segment solid rocket boosters provide the initial violence, the shove that breaks the pad's grip. When they ignite, the sound is not just heard, it is felt as pressure in the chest and as vibration in the ground. Solids are simple in concept and unforgiving in practice. Once lit, they do not negotiate, so their reliability is engineered through materials, geometry, and inspection. The propellant grain shape determines how thrust rises and falls, and tiny voids or cracks can become catastrophic. Quality assurance becomes a safety system because there is no throttle to correct a mistake. The booster's segmentation adds another layer of engineering discipline. Joints must remain sealed under pressure and heat, and the structure must remain aligned under thrust. The memory of earlier failures in solid motor history is never far away, and it shapes how modern boosters are designed, tested, and certified. In a crewed system, the past is not nostalgia, it is a database of consequences. Together, core, stage, and boosters create a short window where the vehicle is most vulnerable. Max Q, vibration, acoustics, and thermal loads stack at once. Max Q is not just a number on a screen. It is the point where aerodynamic forces peak, when the vehicle is moving fast enough for air to become a hammer. In that regime, the rocket is both a vehicle and a resonant structure. Shock waves ripple along the body, and the engine's thrust oscillations couple into the stack. Acoustic energy reflects off the launch pad and surges back toward the vehicle, testing insulation, panels, and avionics housings. The guidance system must keep pointing stable while the entire structure tries to flex. This is the paradox of deep space safety, and it is a hard one to accept. To reach a safer trajectory, the crew must survive the most aggressive minutes of the entire mission. The ascent is a concentrated trial, a compressed storm that must be endured before the long, quiet exposure begins. SLS Block 1 is not optimized for elegance, and it does not pretend to be. It is optimized to throw Orion and its service module onto a trans-lunar path with margin, not with minimalism. Margin means performance reserve, structural reserve, and operational reserve, all held in reserve against the unknown. In deep space, unknowns are not rare. They are the default. That margin is a philosophical break from Apollo's thin trade-offs. Apollo was a sprint, designed under geopolitical pressure and built with a tolerance for risk that history can now measure. Artemis assumes repetition, and repetition demands hardware that can be certified, rebuilt, and trusted. Repetition also demands that the supply chain can keep up, and that procedures can be taught, audited, and improved. The ascent is also a lesson in systems coupling, because nothing operates alone. Guidance, propulsion, structures, and avionics must agree in real time, or the vehicle becomes its own hazard. A guidance correction changes loads, loads change sensor readings, and sensor readings feed back into control laws. Stability is therefore a negotiated state, maintained by software and physics together. After staging and orbit insertion, the character of risk changes, and the soundtrack changes with it. The violence fades, and the long exposure begins, where the spacecraft becomes a moving habitat. The view out the window is calmer, but the environment is harsher in its own way. Time becomes the new adversary, because time multiplies small threats into meaningful ones. Orion is the crew's deep space shelter, not a roomy home, and its interior makes that clear. It is a compact pressure vessel designed to keep biology stable while physics tries to destabilize it. The cabin must hold pressure, remove carbon dioxide, manage humidity, and keep temperature within narrow human limits. Each of those functions is ordinary on Earth, but in space they are active engineering problems. Its volume is larger than Apollo's, but the constraint is still mass. Every extra cubic foot must be justified against propellant, shielding, and structural strength. A larger volume can reduce crew stress and improve work efficiency. Yet it also increases surface area that must be insulated and protected. The capsule's shape is therefore an argument between comfort and physics. Thermal extremes define the cabin's quiet struggle, even when everything looks still. In sunlight, surfaces can heat rapidly, and in shadow, temperatures can fall toward deep cold. With no air outside to carry heat away, thermal control depends on radiation, conduction, and carefully managed internal airflow. The spacecraft must move heat from electronics and bodies to radiators, then reject it to space. Visually, the exterior tells that story in textures. Sunlit panels gleam, while shaded areas look matte and dark, as if they are swallowing light. The spacecraft rotates and slews, and the thermal environment changes with every attitude adjustment. A small change in pointing can shift which surfaces bake and which surfaces freeze. Apollo-era assumptions were shaped by short missions and different electronics, and those differences matter. Apollo's computers were limited, and its data needs were modest by modern standards. Artemis assumes longer operations, higher data rates, and a tighter integration of software with survival. More sensors and more computation can improve safety, yet they also add heat, power demand, and complexity. Radiation drives the most uncomfortable trade because it resists simple solutions. Shielding helps, but mass is expensive, and some materials create secondary particles that complicate the dose. High-energy cosmic rays can strike shielding and generate showers of fragments, which can still penetrate tissue. The goal becomes dose management, not total elimination. So Orion treats radiation as an operational problem as much as a structural one. The design emphasizes monitoring, forecasting, and places to shelter when the sun becomes hostile. Space weather forecasting watches for solar flares and coronal mass ejections, which can accelerate particles toward the spacecraft. When alerts come, The crew needs procedures that are immediate, clear, and rehearsed. The crew module's structure and internal layout reflect that logic, even in details that are easy to miss. Systems are arranged to preserve a survivable core, even when peripheral functions degrade. Dense equipment, water stores, and supplies can be positioned to add shielding in specific directions. In an emergency, the cabin becomes a map of safer and less safe zones. Redundancy is not a luxury in deep space, and it is not just duplication for comfort. It is the only way to keep a single fault from becoming a mission-ending cascade. Redundancy also includes separation. So that one event does not disable all copies at once, the design must anticipate common cause failures, the kind that strike multiple systems together. Orion's computing architecture is built around that idea, and it takes a conservative view of truth. Dual vehicle management computers run in parallel, checking each other and preserving control authority. If one computer diverges, the system can detect disagreement and shift to a safer mode. The crew needs the machine to be skeptical, because deep space is full of subtle corruption. The data network uses time-triggered gigabit Ethernet to make timing predictable, even under stress. Predictability matters when a stray particle can flip a bit and create a phantom command. A time-triggered network schedules communication in fixed windows, reducing jitter and avoiding unpredictable traffic bursts. In plain terms, it keeps the spacecraft from talking over itself when timing matters. Single event upsets are not rare anomalies beyond the magnetosphere. They are a background condition that forces software to behave like a skeptical pilot. A high-energy particle can strike a memory cell and change a value, turning a correct number into a dangerous one. The system must detect those changes, correct them, and keep going without drama. Layered autonomy is the answer, and it is more than a marketing phrase. The spacecraft must detect corrupted states, isolate them, and continue operating without waiting for Earth to notice. Earth is far enough away that even light-speed communication introduces delay, and that delay can grow as the trajectory extends. Autonomy becomes the difference between a transient glitch and a cascading failure. A backup vision processing unit adds another layer of resilience, and it supports both navigation and awareness. Vision supports navigation and situational awareness when other sensors saturate or drift. Cameras can track stars, recognize the moon's limb, and provide relative motion cues during critical phases. If a sensor disagrees, vision can serve as an independent witness. This is not about replacing the crew, and it is not about turning humans into passengers. It is about giving the crew a machine that stays coherent when radiation tries to turn computation into noise. The crew's cognitive load is already high during anomalies, and a confused spacecraft would be an extra adversary. Reliability here is psychological as well as technical. Communications are the next survival system, and they reveal how alone deep space can feel. In low Earth orbit, contact feels constant, and bandwidth feels like a convenience. In cis-lunar space, it becomes a lifeline. The voice loop is not just conversation, it is a safety net of expertise, procedures, and shared situational awareness. Artemis II treats communications as infrastructure, not as a broadcast. The mission is designed to prove a high-reliability template that future lunar operations can inherit. That template includes antennas, protocols, scheduling, and ground staffing, all tuned for continuity rather than spectacle. When something goes wrong, the ability to move data quickly becomes time itself. That template has a hard edge behind the moon, where physics imposes silence. The so-called dark side is not mystical, and it is not permanently dark. It is geometry, a line of sight problem that turns radio into silence. The moon blocks direct transmission, and the spacecraft's signals simply cannot bend around rock. When Orion passes behind the lunar limb, Earth disappears as a relay. The crew must operate through planned loss of signal, and the spacecraft must stay stable without conversation. The timeline becomes a choreography of preloaded commands, expected attitudes, and carefully bounded activities. Even routine tasks feel different when no one can answer back. Visually, this is one of the chapter's most haunting moments. The Earth shrinks into a bright coin, then slips behind the moon's edge as if a curtain is drawn. The radio quiet is not a drama added for effect. It is the natural consequence of orbital motion, and it is unavoidable. This is where autonomy and communications become one story, because blackout is a test of both. A vehicle that cannot manage itself during blackout cannot support far-side science or far-side construction. Stability during loss of signal is not only about attitude control, it is about power management, thermal balance, and fault response without human guidance from the ground. Artemis II's promise is therefore larger than a flyby, even if the trajectory looks simple on a map. It is a rehearsal for a cislunar network that can support crews, robots, and logistics with minimal fragility. The mission asks whether the system can behave like infrastructure, not like a one-time expedition. The difference is subtle, and it is decisive. Optical communications is the sharpest expression of that goal, and it changes what contact can mean. Orion will test O2O, an infrared laser link that treats data as a beam, not a broadcast. Radio spreads energy wide, while laser concentrates it into a narrow path. Concentration enables higher data rates, but it demands precision. The mascot terminal is designed to lock onto ground stations with remarkable accuracy. In ideal conditions, it can push data rates toward 260 megabits per second. That capability depends on pointing stability, fine tracking, and a clean optical path through the atmosphere. It is like threading a needle from hundreds of thousands of kilometers away. Bandwidth changes exploration because it changes decision speed, and decision speed changes safety. High-rate telemetry reveals subtle trends early, before they become alarms. A slow temperature drift in a component or a slight change in power draw can be seen as a pattern rather than a surprise. The earlier a pattern is recognized, the more options exist. Bandwidth also changes public meaning without being the point, because it changes what can be shared. Live 4K, richer audio, and continuous health data make deep space feel less distant and less forgiving. The audience sees not only the beauty, but the constraints, the checklists, and the quiet discipline. Exploration becomes legible, and that visibility carries its own pressure. But lasers have their own vulnerability, and it is not an engineering flaw so much as a reality of air. Clouds can break the link, and atmosphere becomes a variable that must be engineered around. Turbulence can distort the beam, and moisture can absorb or scatter photons. The system must therefore assume imperfect skies, not ideal ones. So the ground strategy becomes planetary scale, because redundancy is not only on board. White Sands and Table Mountain provide geographic diversity, reducing the chance that weather silences the mission. When one site is clouded out, another may be clear, and the network can hand off the link. The Earth itself becomes part of the communications architecture. This is communications as a distributed system, with redundancy across continents and across technologies. It is the early shape of an interplanetary internet, built from stations, protocols, and trust. Trust here means verified timing, authenticated commands, and predictable performance under stress. A communication system is only as safe as its ability to resist confusion. The same logic extends to navigation and timing, because location is a safety parameter. Deep space forces the vehicle to know where it is without depending on constant correction from Earth. In low orbit, tracking assets can update state vectors frequently. Farther out, the spacecraft must carry more of that responsibility, using star trackers, inertial sensors, and optical cues. Orion's sensors and cameras are not only for documentation, and they are not only for public images. They are instruments for reading the moon as an archive, and for validating how humans interpret that archive. A calibrated camera can measure brightness and texture, while a trained eye can notice anomalies that algorithms might miss. The mission tests both the instruments and the interpretation pipeline. The Moon is a recorder of solar system history because it lacks erasing processes that Earth takes for granted. Its surface holds impact statistics, solar wind implantation, and radiation exposure in place. With no active plate tectonics and no global weather, scars remain for billions of years. Each crater is a time-stamped event, written in rock. Visually, that record is written in contrasts. Rays of bright ejecta stretch across darker plains, and ancient highlands look battered like hammered metal. The Terminator line, where day meets night, throws long shadows that reveal relief. In those shadows, the Moon looks less like a sphere and more like a landscape. Artemis II will not land to sample that record, and it will not drill into layers. It will still observe it with modern sensors, and it will test how quickly data can be returned and understood. The ability to capture, compress, transmit, and analyze images is part of the science story. Science becomes an operational workflow, not just a set of instruments. Far-side views matter in this context, and not only because they are rare. The far side is not just unseen, it is different in crustal thickness and Mera distribution, and it raises questions about formation and evolution. The near side's broad basaltic plains contrast with the far side's rugged highlands, a difference that still invites competing explanations. Seeing it well requires stable pointing, calibrated cameras, and reliable downlink all at once. The science is tied to the same communications geometry that creates operational risk. A blurred image can be a pointing issue, a vibration issue, or a data loss issue, and each has different implications. The spacecraft becomes the mediator between observation and interpretation. The spacecraft is therefore a bridge between cosmology and logistics, and the bridge must be strong. It carries humans to a place that preserves violence, and it carries data back fast enough to matter. The Moon's surface is a museum of impacts, yet the mission's success depends on mundane things like connectors and timing. That tension is the true mood of deep space. Manufacturing is the quiet prerequisite that makes this repeatable, and repeatability is the real ambition. Artemis cannot become infrastructure if each vehicle is a bespoke artifact that takes a decade. Infrastructure implies cadence, and cadence implies processes that can be repeated without losing quality. The factory floor becomes as important as the launch pad. Orion and its subsystems increasingly use 3D printed parts where qualification allows, and qualification is the key phrase. Additive manufacturing shortens supply chains and enables rapid redesign after test findings. It can also produce geometries that traditional machining struggles to create, such as internal channels and optimized brackets. Yet every printed part must prove it can survive vibration, thermal cycling, and vacuum. Augmented reality assembly tools reduce human error during integration, and integration is where complexity concentrates. They turn complex routing and torque sequences into guided procedures that can be audited. A technician sees overlays that confirm connector orientation, fastener selection, and cable paths. The result is not automation replacing skill, but skill being supported by structured verification. Selective reuse from Artemis I is part of the same sustainability logic, and it is more subtle than it sounds. Reusing qualified components reduces cost, but it also preserves lessons embedded in hardware. A flown component carries a history of stresses and environments that can be analyzed and compared to models. That comparison improves confidence, and it refines future design margins. This is not reuse as nostalgia, and it is not reuse as a museum practice. It is reuse as an engineering strategy to keep cadence possible when budgets and suppliers become constraints. The goal is to avoid a fragile pipeline where one missing part delays a mission by years. Sustainability here means operational continuity, not just financial efficiency. The European Service Module is the clearest example of coalition architecture, and it changes the mission's anatomy. It provides propulsion, power, and consumables, acting as the mission's lungs and bloodstream. The crew module is the shelter, but the service module is the metabolism. Without it, the capsule is a sealed room with no endurance. Propellant in the ESM enables major maneuvers and fine attitude control, and those are not optional. Consumables support the crew's metabolism, and solar arrays keep the electrical system alive. Power is needed for thermal control, computing, and communications, which are all survival functions. In deep space, electricity is not convenience, it is life support by another name. Visually, the ESM's solar arrays extend like dark wings, catching sunlight with a quiet efficiency. Their orientation matters, because power generation depends on angle and shadowing. Attitude control becomes a negotiation between pointing for communications, pointing for thermal balance, and pointing for power. Every subsystem has a preferred direction, and the spacecraft must satisfy them all. Europe's role is not symbolic, and it is not merely political theatre. It is functional dependence, and dependence forces interoperability to become real rather than diplomatic. Interfaces must match, procedures must align, and engineering cultures must translate across languages and standards. The result is a system that is tested not only in vacuum chambers, but in meetings and documentation. The ESM also carries a main engine with a lineage that reduces risk. And lineage is a form of evidence. Its heritage traces to the Space Shuttle's OMS engine family, chosen because proven systems narrow uncertainty. A main engine is not used continuously, but when it is needed absolutely. Heritage provides confidence that ignition, thrust, and shutdown behavior are understood. That choice reflects a deeper Artemis pattern, and it is a deliberate one. New capabilities are introduced where they change the future, while critical life and return functions lean on known behavior. Optical communications can be tested because radio still exists as a backup. Manufacturing can evolve because structural margins are still conservative. Innovation is invited, but it is bounded. SLS provides the energy to escape Earth's gravity well, and it does so in a few minutes of controlled violence. Orion provides the shelter to survive the exposure that begins once Earth's field no longer dominates. Between them sits a philosophy of layered survival, expressed in hardware and in procedures. The machine is not one machine, but a stack of agreements. Redundant computers, hardened networks, and diversified communications are treated as life support, not as optional sophistication. They exist because deep space punishes single points of failure. A single corrupted packet, a single misread sensor, or a single missed thermal limit can become a chain. The system is designed to break chains before they form. This is why Artemis II feels like a race, even when it looks cautious. And the race is against ignorance. The program is racing to validate a template before deep space punishes delay with accumulated unknowns. Every year without flight is a year without data. And data is the only antidote to uncertainty. The moon is close enough to reach, yet far enough to teach. The template is not only a vehicle, and it is not only a trajectory, it is an operational stack that includes manufacturing cadence, coalition interfaces, autonomous fault management, and high bandwidth links. It also includes training, simulation, and the discipline to treat anomalies as expected rather than shocking. A template is a promise that the next mission will not start from zero. If it works, the moon becomes more than a destination and more than a symbol. It becomes a node, a place where far-side operations and surface systems can be coordinated reliably. A node implies traffic, schedules, and sustained presence. It implies that missions can build on each other rather than merely echo each other. If it fails, the lesson is not just technical, and it will not stay contained. It is cosmological, a reminder that Earth's magnetic cradle is not a default condition of the universe. The conditions that make human life easy are local and temporary, and they do not travel with us. The spacecraft must carry the rules of survival into places that do not offer them. The central question sharpens here, and it is as much philosophical as it is engineering. Artemis II is racing because the space between worlds is where systems either become resilient or reveal that they never were. What does it mean to build a habitat that can argue with radiation, silence, and time, and still win? The answer will not be spoken. It will be demonstrated. Next, the story moves from the ship to the journey it must execute. We follow the mission profile as a chain of commitments, where each burn and blackout tests the blueprint. Chapter 1 named the hostile environment beyond Earth's shield, where radiation and vacuum punish every assumption. Chapter 2 trained humans to endure it, because biology is fragile even when technology is strong. Chapter 3 built the ship, assembling metal, software, and procedure into something that can leave home. Chapter 4 asks if the ship can survive coming home. Artemis II is framed as a deep space mission, yet its hardest physics waits in air, not emptiness. The moon is distant, but the atmosphere is the knife edge where energy must be paid back. Returning from the moon is an entry energy problem disguised as a navigation problem, because the path is only the prelude. The real equation begins when Earth grows large in the window and velocity refuses to be negotiated. In the visuals, the capsule is small against the planet, a dark seed falling toward blue and white. The camera would linger on that thin, atmospheric limb, an almost invisible line that becomes a furnace in seconds. It looks gentle from orbit, like haze over an ocean, yet it is a compressible fluid waiting to be shocked. What does it mean that the most dangerous part of a lunar mission is the last few minutes above the Pacific? Artemis I came back fast and clean on paper, then left a troubling signature in Avcode when the hardware was finally opened. Engineers expected smooth, predictable ablation and a uniform recession pattern across the shield's tiled honeycomb. They found gouging, unexpected material loss, and crater-like cavities that did not fit the model's story. The post-flight photography was clinical and unsettling, pale, scorched textures interrupted by pits that looked punched rather than worn. Normal ablation is controlled sacrifice, where the heat shield erodes in a managed way while keeping the structure behind it cool. The surface chars, recedes, and carries heat away with consumed material, turning kinetic energy into chemistry. Spalling is different, because it is not gradual thinning but sudden chunk loss. Spalling is a mechanical failure mode that removes protection faster than planned, and it can do so unevenly across a surface. That distinction matters because entry heating is not linear, and margins are not evenly distributed. A small local defect can become a hotspot, and a hotspot can become a runaway when the surrounding flow reorganizes. In a wind tunnel sense, the shape of the heat shield is part of the aerodynamics, not only a thermal layer. When a chunk disappears, the airflow and heating can change in the same instant. The mystery mattered because Orion's heat shield is not just thermal protection, and it is not merely a replaceable skin. It is a structural boundary between plasma and crew survival, a pressure wall that must remain intact while everything outside becomes luminous. A small change in how it fails can create a new loss of crew pathway, even if the average performance looks acceptable. In human spaceflight, the average is never the question, only the worst credible case is. Avcoat is a filled epoxy novolac with a honeycomb structure that holds it in place and controls how it cracks. The honeycomb is not decorative, and it is not simply for manufacturing convenience. It creates cells that limit crack propagation, so damage does not easily spread like a tear in fabric. Under hypersonic heating, Avcoat does not simply burn away like wood, because it is engineered to decompose in stages. It undergoes pyrolysis, breaking down chemically and generating gases inside its porous matrix as long polymer chains fracture. Those gases are not smoke in the everyday sense, but a mixture of decomposition products that expand as they heat. The chemical reaction absorbs energy, which is one reason ablators work at all. In plain language, the material spends heat to destroy itself in a controlled way. Those pyrolysis gases are part of the design, not a side effect to be tolerated. gas flow through pores can carry heat outward and help form a protective boundary layer near the surface. The char layer can insulate like a ceramic blanket, while the surface ablates and sheds energy into the flow. In the right regime, the shield is not only resisting heat, it is actively managing it. But porosity is a double-edged parameter that couples chemistry to mechanics, and it does so without asking permission. If pores connect poorly, gas can become trapped, and pressure can rise locally behind a stiffening char layer. If pressure rises faster than it can vent, the material can fracture and eject chunks, converting a thermal design into a structural problem. The shield is, in a sense, trying to breathe while being squeezed. Hypersonic entry adds another complication that feels almost like cosmology, because familiar air becomes unfamiliar matter. At lunar return speeds, the shock layer becomes so hot it ionizes air into plasma, stripping electrons from molecules. Plasma is not fire, yet it behaves like a conductive fluid that can intrude through gaps and carry energy in new ways. The capsule is not burning in oxygen. It is plowing through a shocked, electrically active sheath. The heat shield is therefore fighting multiple antagonists at once, and each antagonist speaks a different language. It is fighting convective heating from compressed air, where molecules slam into the surface and transfer energy. It is fighting radiative heating from the shock layer, where excited species emit light that becomes heat when absorbed. It is fighting internal gas dynamics that can turn chemistry into cracking, especially when the material's microstructure is not behaving as predicted. Artemis I's cavities suggested a mismatch between predicted and actual internal pressure behavior during the hottest part of entry. Some locations lost more material than the surrounding region could explain, as if the shield had been struck from within. The pattern hinted at localized mechanical failure, not uniform thermal recession, and that implication changes how you test. If the failure is internal, surface temperature alone cannot tell the story. NASA's investigation treated the anomaly like a crime scene, with physics as the suspect and data as the witness. They mapped the damage, correlated it with the entry timeline and heating rates, and compared it to arc jet tests that simulate hypersonic heating. They asked whether the failure began at the surface or inside the material, because the mitigation depends on that first moment. A crater is an outcome, but the cause is a sequence. The visuals here would be methodical. Technicians in clean room suits, the shield rotated under structured light, every cavity measured. Close-ups would show the honeycomb pattern beneath char, like a grid revealed by erosion. Overlays would animate the entry timeline, letting the audience see when heating peaks and when pressure might build. The shield becomes a map, and the map becomes a question. One hypothesis centered on the relationship between manufacturing and verification, because the process is as real as the design drawing. Orion's AVCOAT process had been updated to reduce porosity and improve ultrasonic inspection, which is how hidden voids can be detected. Lower porosity can make defects easier to detect and can improve bond consistency between AVCOAT and the underlying structure. In production, predictability is safety, and inspection is the language of predictability. Yet changing porosity also changes how pyrolysis gases move, and flow paths are part of the thermal design. Reduced pathways can increase local pressure during peak heating, especially when the char layer stiffens and permeability drops. A process meant to improve confidence can unintentionally shift performance under the most extreme conditions. The uncomfortable truth is that better in one metric can be worse in a different regime. This is the uncomfortable engineering truth of human rating, and it has a long history in aerospace. You do not only certify the design, because the design is an abstraction until it is built. You certify the as-built process, because the process becomes the material, and the material becomes the mission. The Apollo era learned this lesson repeatedly, when small manufacturing variations created large flight consequences. The stakes were not academic, because spalling changes failure margins quickly and without graceful warning. If chunk loss exposes underlying structure, heating can accelerate in ways models did not bound, because the surface chemistry changes abruptly. The crew module's aluminum structure is not meant to see plasma directly, and it is not meant to become part of the heat shield. A shield that becomes thin is one problem. A shield that opens is another. Aluminum exposure is a direct loss of crew pathway, because aluminum melts and weakens at temperatures far below plasma conditions. A burn-through is not a slow leak that can be managed with procedure and time. It is a catastrophic breach that turns cabin pressure into vacuum, and it does so while the vehicle is still under extreme aerodynamic load. The crew would have no meaningful escape option in that phase. Spalled chunks also become debris in the wake, and debris has its own chain of risk that is easy to overlook. Orion's parachutes deploy late, yet they deploy into a disturbed flow field that is still settling from entry dynamics. A liberated fragment can strike lines, canopy fabric, or mortar covers at the wrong moment, turning a thermal anomaly into a landing anomaly. In systems engineering, failures migrate across subsystems like weather. Even if the heat shield survives, entry can threaten other interfaces that sit near the boundary of the shield. Bolts and fasteners near the shield perimeter can heat and lose strength, especially if local flow concentrates. Gaps can widen, and plasma can intrude into seams that were never supposed to see ionized flow. A seam is a geometric fact, and geometry is what hypersonic flow exploits. Plasma intrusion is not just a thermal problem, and it is not limited to scorching. It can be an electrical problem, because plasma conducts and can couple into wiring or create unexpected current paths. Entry is where thermal, mechanical, and electrical domains collide in a compressed timeline, leaving little room for diagnosis. The environment does not separate disciplines, even if organizations do. NASA had a schedule dilemma that was also a philosophical dilemma, because both options carried real cost. Replace the heat shield and accept a major slip, or keep the hardware and change how it is used. The program's race was not toward the moon alone, and it was not only about a single launch. It was toward a credible cadence before budgets and geopolitics reshaped the plan. A full heat shield replacement is not like swapping a panel, and it is not a clean reset. It is a major rework with long lead times, new inspections, and new uncertainties introduced by disassembly and reassembly. It also risks introducing new defects while chasing the old ones, because every touch is a chance to change the system. In aerospace, rework is sometimes safer than flight, yet it is never free of risk. So the program looked for an engineering solution that lived in trajectory, because trajectory is a knob you can turn late. If physics is the antagonist, then flight profile is the negotiation, and negotiation is sometimes all you have. You cannot change the atmosphere, but you can choose how you meet it and how long you stay inside it. The capsule cannot bargain with heat, but it can choose the terms of exposure. Orion's baseline design included a skip entry capability, a technique with heritage in lifting bodies and earlier capsule studies. Skip entry uses lift to dip into the atmosphere, climb back out, then re-enter again, trading peak loads for time. It spreads heating across 2 pulses and reduces peak deceleration, like skipping a stone across water. In a diagram, the path looks elegant, almost gentle, as if the capsule is testing the air before committing. But skip entry has a hidden cost in thermal soak time, and soak is where chemistry becomes destiny. 2 heat pulses mean the structure stays hot longer, and heat can conduct deeper into the shield and its bonds. A longer exposure can give pyrolysis gases more time to build pressure behind a char layer, especially if permeability changes mid-flight. The shield may tolerate a peak, yet fail under duration. Ballistic entry is the simpler profile, with a single deeper plunge and one main heating pulse that is intense but brief. It can raise peak heating and peak G-load, yet it shortens the time the shield spends in the critical temperature band. It is like touching a hot pan briefly instead of holding your hand near it, where time becomes the injury. The body can survive a spike that it cannot survive as a sustained condition. Thermal soak is the enemy of margins that rely on time-dependent chemistry, and ablation is deeply time-dependent. Heat penetrates by conduction, and conduction is slow but relentless, moving inward even when the surface is shedding material. If you keep the material hot longer, deeper layers begin participating in the failure physics, and those layers were not meant to be active. The shield's protective behavior is a race between decomposition, venting, and structural integrity. NASA's choice was a controlled gamble that traded one risk shape for another, and the trade was explicit. They leaned toward a single-pulse ballistic entry to reduce the duration of internal pressurization conditions that might drive spalling. They accepted higher peak loads in exchange for less time at damaging states, and that acceptance had to be justified quantitatively. In human spaceflight, risk is not embraced, it is bounded, documented, and argued. This was not a decision made by intuition or bravado, even if it can look like boldness from the outside. It was grounded in test data, models, and a bounded set of acceptable outcomes that could be verified. The goal was not to eliminate risk, because lunar return cannot be made risk-free by declaration. The goal was to move risk into a region that could be tested, measured, and defended. The decision also reframed the mission's meaning, because Artemis II is not only testing deep space operations, it is testing whether engineering can outmaneuver an anomaly without rebuilding the vehicle, which is a different kind of competence. It is testing whether trajectory can be treated as hardware and whether operations can be treated as design. When does a flight rule become as important as a bolt? The heat shield story also teaches a cosmology-adjacent lesson about where danger truly lives, and it is not where intuition points. Space feels empty, but entry proves the universe is not only vacuum hazards and radiation belts. The boundary between worlds is where energy is cashed out, and that cash-out is atmospheric. The thin line that protects life is also the line that punishes speed. At lunar return velocity, air becomes a compressible medium that behaves like a different substance, with properties that feel almost alien. It forms a shock wave that converts kinetic energy into heat, because the air cannot move aside fast enough. That heat creates plasma, and plasma creates a radio blackout that is not a communications failure. It is a physics signature, a visible reminder that the rules have changed. The blackout is a reminder that the capsule is briefly wrapped in a sheath of ionized gas, like a cocoon made of charged particles. Signals cannot pass through easily because electrons absorb and reflect radio waves in the frequencies used for communication. The crew is isolated at the exact moment the environment is most violent, hearing only onboard tones and feeling only acceleration. In that silence, trust becomes a system requirement. Ablation chemistry becomes the quiet hero in that moment, working without moving parts and without software. Pyrolysis creates char. Char insulates, and gas flow can cool the surface by carrying energy away into the boundary layer. But if gas cannot escape, it becomes a wedge that pries the material apart, turning protection into vulnerability. The same mechanism that helps can also harm, depending on microstructure and time. Spalling, therefore, sits at the intersection of chemistry, porosity, and mechanical stress, and it refuses simple explanations. It is not only about temperature, and it is not only about material choice or thickness. It is about how a material breathes under pressure while being cooked at hypersonic speed, and how that breathing changes as it chars. The shield is a chemical reactor, a pressure vessel, and a structural shell at once. As the heat shield investigation unfolded, another crisis emerged in a different domain, and it arrived without dramatic imagery. It was not dramatic in photos because it lived on circuit boards and in transient waveforms. It threatened the same thing as the heat shield, though by a quieter route. It threatened the crew's ability to keep breathing, minute after minute, when no outside help exists. Orion's ECLSS is a network, not a box, and networks fail in patterns that can surprise. Fans move air so CO2 does not pool. Valves route flow so scrubbers can do their work. Sensors confirm pressure and composition, and controllers coordinate motors. A fault in one controller can propagate because life support depends on coordinated motion and correct feedback. The system is less like a machine and more like a small, regulated ecosystem. The electronics issue centered on motor controller boards and an invisible behavior called back EMF, a basic consequence of electromagnetism. When a motor is switched or decelerated, it can generate voltage back into the circuit as magnetic fields collapse. If the circuit cannot absorb that energy, voltage spikes can exceed component limits and damage electronics. In plain terms, the motor can kick back like a spring, and the board has to catch it. In deep space, a hard failure is not a reset and a shrug, because redundancy is finite and time is unforgiving. A hard failure can mean a stuck valve, a dead fan, or a disabled pump that cannot be coaxed back. It can mean CO2 removal degrades, humidity rises, and crew cognition erodes before alarms feel urgent. The danger is not theatrical, it is physiological and slow. The risk was existential because ECLSS failures can be deceptive and the body is not a perfect sensor. Humans can feel fine while CO2 climbs, then become impaired in judgment, attention, and decision-making. A system meant to preserve life can become the source of subtle confusion. And confusion is how mistakes compound. How many spacecraft failures begin not with panic, but with a slightly dulled mind? NASA's fix was conceptually simple and operationally heavy, because simple physics still demands rigorous proof. They added resistors and capacitors to manage transient energy and clamp voltage spikes, shaping the waveform into something components can tolerate. They changed the circuit's response to switching events, turning a potential spike into a damped pulse. The board would still see the kick, but it would feel it as a controlled push rather than a blow. Then came recertification, because deep space hardware is guilty until proven stable, and stability must be demonstrated under stress. Boards were tested in vacuum, where heat dissipation changes and arcing behavior differs, and where convection cannot save you. They were vibrated because launch loads can crack solder joints and loosen connectors in ways microscopes must later explain. They were cycled and monitored because intermittent faults are the most dangerous kind. The lesson is that invisible electrical behavior becomes visible only when it kills something, and aerospace tries to learn earlier. Back EMF is just physics, like plasma and pyrolysis, and it does not care about intent. It does not care that a schedule is tight or that a mission is historic, because electrons follow fields. The universe is consistent, which is both its cruelty and its gift. The program now had stacked risks, not isolated ones, and stacking changes how managers think. Heat shield uncertainty sat beside life support electronics, and each demanded resources, test time, and attention. Other readiness hurdles pressed in at the edges, because large systems fail by accumulation rather than by a single dramatic flaw. When many small uncertainties coexist, the probability of an ugly interaction rises. Batteries raised questions about performance and qualification margins, because energy storage is chemistry under discipline. A battery is stored chemical potential, and it ages even when unused through slow side reactions and material changes. If capacity or internal resistance drifts, power budgets tighten and thermal control becomes harder, especially in cold soak conditions. A battery that is slightly weaker can force other systems to operate closer to their limits. Helium leaks added another classic propulsion concern, because small molecules find paths that engineers wish did not exist. Helium is used to pressurize propellant systems, and leaks can be slow until they are not, especially as temperatures change. A small leak can become a countdown scrub, then become a schedule slip that ripples across suppliers and teams. The leak itself may be minor, yet the programmatic shock can be large. ICPS issues added another layer of integration pressure, because the interim cryogenic propulsion stage is the bridge between launch and mission geometry. The stage must perform reliably to place Orion on the right path, with the right timing and margins. If the stage has anomalies, the mission's corridor narrows and contingency options shrink because fuel and time are not infinite. A deep space mission begins with a precise push, and precision is unforgiving. Flight readiness is therefore not a single green light, and it is not a simple checklist moment. It is a logic problem that weighs interacting uncertainties, each with different evidence and different consequences. It asks whether remaining risks are understood, bounded, and mitigated by design or procedure. It also asks whether the unknowns are independent or whether they might align. NASA's approach was not to pretend these problems were independent, because independence is often a comforting fiction. They treated them as coupled constraints on a timeline, where mass, power, and schedule trade against one another. Fixing one issue by adding mass, time, or complexity could worsen another margin, and the system would still have to close. Engineering becomes the art of not solving one problem by creating two. This is where the theme of racing becomes sharper and more mysterious, because the race is not only against a date, the race is not a sprint toward a launch date for its own sake, and it is not merely a public milestone. It is a controlled gamble against time, budgets, and geopolitical momentum, all of which shape what can be tested. The spacecraft is built in a world with politics, yet it flies in a world without them. Time is an engineering variable, because delay changes hardware state in ways that are subtle but real. Components age, suppliers shift, software baselines evolve, and teams lose continuity as people rotate. Budgets are not just money, and they are not only spreadsheets. They are the ability to keep expertise intact and processes stable, so lessons do not evaporate. Geopolitical momentum is not a subplot, because it shapes what gets funded and what gets repeated in future years. A program that slips too far can be reframed as optional, and optional programs are fragile. A program that flies can become infrastructure by default because success creates its own arguments. The flight is not only a mission, it is a claim that the architecture is real. Yet none of those pressures can override the universe's constraints, because physics is not persuaded by urgency. Hypersonic plasma will form at lunar return speeds, regardless of speeches and schedules. Pyrolysis gases will be generated inside AVCOAT under heating, regardless of how confident the models feel. Back EMF will appear in motors when they switch, regardless of how carefully meetings are run. Artemis II's engineering response is therefore a negotiation with immutable physics. And negotiation requires evidence. It uses test data to choose a trajectory that reduces soak time and changes failure likelihood, rather than pretending the anomaly never happened. It uses circuit changes and qualification to turn transient spikes into manageable behavior, rather than trusting luck. The mission becomes a set of bounded bets, each one argued with numbers. This is crisis engineering as a discipline, not crisis engineering as improvisation or heroics. It is the art of choosing which uncertainties to carry into flight and which to eliminate on the ground. It is the practice of keeping the unknowns from aligning into a single fatal chain, because chains are how disasters form. The work is quiet, procedural, and relentless, yet it is also creative. The heat shield decision also reframes how we think about the moon's distance, because distance is not just miles. The mission is not only about reaching the lunar neighborhood and proving navigation and communications. It is about returning through Earth's atmosphere with lunar energy still in the vehicle's velocity. The moon lends you speed on the way home, and Earth demands payment with heat. That return is a reminder of Earth's dual role in the central question, and the dual role is almost poetic. Earth is cradle and shield, yet it is also a barrier that must be crossed violently when you come back. The atmosphere that protects life is also the medium that can destroy a spacecraft, because protection is not gentleness. The same gas that softens sunlight can harden into plasma under shock. In cosmological terms, this is a boundary condition that shapes expansion, and it applies to any world with air. Any species leaving a planet must solve both vacuum survival and atmospheric entry, and both require different kinds of mastery. The architecture of interplanetary life must include reliable re-entry, not just reliable launch, because travel is a loop. If you cannot close the loop, exploration becomes exile. Artemis II is racing to prove that architecture can be repeatable, and repeatable is the real standard. Repeatable means anomalies are investigated without paralysis, because paralysis is another form of failure. Repeatable means fixes are verified without endless redesign, because redesign can become an infinite project. The program is trying to build not just a mission, but a rhythm. It also means accepting that some solutions are operational rather than structural, and that operations can be engineered. Sometimes you do not rebuild the shield, because rebuilding is not the only path to safety. You change the way you fly the shield through the shock layer, and you validate that change with test and analysis. The flight profile becomes a tool, as tangible as a material coupon. This is not recklessness dressed up as urgency, and it is not faith substituted for analysis. It is risk management under constraints, where the constraints include politics, but are ultimately enforced by physics. The universe is the final reviewer, and it does not accept appeals, extensions, or explanations. It only accepts what works. As launch approaches, the story tightens into a single corridor of commitments, and that corridor narrows with every signature. Hardware is closed out, tests are signed, and waivers are weighed like currency that must be spent carefully. The mission becomes a chain where each link is either strong enough or it is not. In the final weeks, even small changes feel heavy because they ripple. In the visuals, the capsule sits under bright lights, its surface is pristine in a way space will soon erase. Engineers point at screens filled with plots, while technicians torque fasteners that will never be touched again. Outside, the rocket waits like a vertical argument, silent and patient. The atmosphere above it looks calm, which is its most misleading feature. Once the countdown begins, engineering arguments end, and nature's argument begins. The vehicle will meet air at hypersonic speed, and plasma will decide what radios cannot. The crew will trust that crisis engineering turned unknowns into bounded risks, and that the bounds were honest. Transition to flight begins here, because after ignition, the story becomes irreversible. The next chapter follows the mission profile as it leaves Earth's shield and sets up the return that will test every fix. Once the countdown begins, engineering arguments end and nature's argument begins. Artemis II leaves the pad as a clock-driven sequence where every second is already spent. The rocket does not negotiate with opinions because combustion, pressure, and gravity only answer to numbers. On the countdown net, voices sound measured and almost ordinary, yet the vehicle is already transitioning from a construction project into a single, irreversible experiment. Launch day starts hours before ignition, inside a choreography that looks calm because it must. Floodlights wash the pad in hard white, and vapor curls from umbilicals like breath in winter air. Cryogenic fueling turns the rocket into a controlled boil, with tanks kept stable by constant venting. At these temperatures, oxygen and hydrogen are not simply cold, they are near their boiling points, where heat leaks become phase change. That is why the pad seems alive, exhaling clouds that drift, thin, and vanish into the dark. Liquid oxygen and liquid hydrogen are loaded against time, temperature drift, and sensor noise. The propellants arrive through insulated lines, and each valve position is a decision about pressure, flow rate, and thermal shock. The vehicle enters replenish mode, topping off propellant as it warms and flashes to gas. Replenish is not comfort. It is margin management under physics that never pauses. Even with foam, insulation, and vacuum jackets, the environment keeps pushing heat inward, molecule by molecule. A valve timing error or a thermal spike can ripple forward into engine start limits. Sensors must distinguish real trends from the jitter of cryogenic instrumentation, because false alarms waste time and real alarms waste missions. Engineers watch tank pressures, temperatures, and mass estimates, and they compare them to models built from years of ground testing. The rocket's skin looks still from a distance, but inside, fluids are sloshing, stratifying, and venting under carefully tuned rules. The crew suit checks feel ceremonial, yet they are functional barriers against a cabin that is not forgiving. Pressure integrity, comm loops, and biomedical baselines are verified while the rocket is still silent. Each suit is a small spacecraft, with seals that must hold and ventilation that must flow. A microphone check is also a survival check, because a quiet failure can become a loud emergency later. Crew ingress is a ritual that hides razor-thin margins in plain sight. The elevator ride up the tower is slow enough to feel contemplative and fast enough to remind you that the clock is moving. The hatch closes and the cabin becomes a system, not a room. Inside Orion, switches, displays, and circuit protections are arranged for speed, because hesitation is also a form of risk. The crew's posture changes as straps tighten, and the spacecraft's interior becomes less like a cockpit and more like a pressure vessel with responsibilities. At T-minus minutes, the stack transitions from ground control to flight control without drama. That handoff is a boundary crossing, because recovery options shrink with each committed step. Ground umbilicals retract, and the vehicle begins relying on its own power and internal timing. Computers take over sequences that humans cannot execute fast enough, and they do it with a kind of unemotional precision. In the background, range safety and tracking systems shift from observation into readiness, because the rocket is about to become a moving object with consequences. Ignition is not one event, it is a cascade of permissions and confirmations. Valves open in a prescribed order, turbopumps spin up, and sensors look for signatures that match expectation. Engines light, boosters commit, and the vehicle becomes a moving load path. The first moments are a controlled violence, where thrust must rise smoothly enough to avoid shock, yet quickly enough to avoid lingering instability. The pad holds the stack down until thrust and guidance agree that the rocket is truly ready to leave. Ascent physics compresses into a few minutes, where aerodynamics, guidance, and structure must agree. The first enemy is not space, it is air. In the lower atmosphere, density is high, and every steering command is a negotiation with drag, buffet, and heating. The rocket rises through thick atmosphere while acceleration climbs and steering stays precise. From the ground, it seems to climb straight up, but the guidance solution is already bending the trajectory toward orbit. The guidance solution is a narrow corridor that balances gravity loss against drag loss. Point too high and you waste energy fighting gravity because you are climbing without building horizontal speed. Point too low and you plow into dense air, where drag and heating punish every extra second. Guidance algorithms continuously solve for attitude and throttle, using inertial sensors that feel acceleration and rotation as raw physical truth. The crew feels it as a steady push, growing heavier as the vehicle sheds propellant and becomes lighter. Max Q arrives as a peak in dynamic pressure that the vehicle cannot brute force away. Dynamic pressure is density times velocity squared, and the square term is why it rises so sharply. Throttle profiles and attitude hold-downs exist to keep bending and vibration inside limits. The rocket may briefly throttle down, not because it is weak, but because it is being careful. In those seconds, the air is thick enough to hit like a fluid wall, and the structure must remain aligned with its own thrust. At max Q, the stack is a resonant structure that wants to flex and ring. Software fights that tendency with continuous steering, while the crew rides the coupled motion. Vibrations travel through tanks, interstages, and adapters, and they can amplify if frequencies align. Engineers call it loads, modes, and margins, but the experience is physical. Subtle shudders and oscillations that remind the crew they are inside a machine under stress. The rocket's job is not only to generate thrust, but to keep that thrust pointed through a structure that is bending, however slightly, under its own power. Booster separation is timed to the millisecond, because the next stage must inherit a stable vehicle. Separation motors, springs, and guidance logic work together to prevent recontact. The boosters peel away like thrown spears, rotating and falling back toward the ocean, while the core continues forward. This is not a cinematic flourish. It is collision avoidance at high speed. If the departing boosters drift too close, a small contact could become a catastrophic torque on a vehicle still under thrust. Staging is not a pause. It is a handoff of forces and control authority. The chain continues through core stage burn, where propellant flow becomes trajectory. Flow rates, mixture ratios, and chamber pressures are monitored because they are the language of performance. The vehicle is now above much of the atmosphere, but not above consequence, because guidance errors at this point can still compound. The sky darkens to a deep indigo, and the horizon begins to curve, a visual hint that the geometry of the mission is changing. Main engine cutoff ends the core stage's argument with gravity, and the vehicle is suddenly quieter. The silence is deceptive, because orbit is not safety, it is only a new regime. When the main engines shut down, the body expects another push, and the absence feels like a drop. Microgravity arrives not as floating magic, but as the removal of a constant load. The crew's straps, tools, and checklists become objects that must be managed, because nothing stays put unless you make it. Orion and the ICPS settle into initial orbit with a state vector that must be verified. A state vector is position and velocity, and in orbit, those numbers are destiny. Navigation now becomes measurement, not thrust, and measurement must be trusted. Ground radars, onboard inertial units, and star trackers all contribute, and each has its own biases. The mission team compares independent solutions because agreement is confidence and disagreement is a problem to solve quickly. The first orbital shaping burn raises perigee to buy time and reduce atmospheric drag risk. Perigee is the low point, and in a fresh orbit, it can be uncomfortably close to the upper atmosphere. The second burn raises apogee into a high elliptical orbit that creates a deliberate pause. In this stretched ellipse, the spacecraft spends long minutes near apogee, moving slowly, like a pendulum at the top of its swing. That slow motion is useful because it gives time to check systems while the clock is not yet demanding the moon. That high ellipse is not scenic. It is operational breathing room. It provides test time and a safety off-ramp because a return can be executed without committing to the moon. This logic echoes earlier eras of exploration, when ships hugged coastlines until they trusted their hulls and navigation. Apollo missions also used carefully planned orbits and burn sequences, but Artemis inherits a new complexity, more software, more redundancy, and more interfaces that must all agree. The ellipse is a compromise between urgency and caution, written in orbital mechanics. In this orbit, Earth still fills the window, and the comm loop still feels immediate. City lights trace coastlines, clouds swirl in layered spirals, and lightning flickers faintly inside storm systems. Yet the mission is already preparing to leave Earth's shield, where the rules become less kind. The magnetosphere is not a wall, but it is a broad deflection system that reduces the worst of charged particle flux. As Orion climbs outward, that protection thins, and the environment begins to resemble deep space rather than near-Earth routine. The first 24 hours are a systems validation campaign disguised as routine. The crew transitions from launch posture to habitation posture because endurance is the mission's true payload. They move slowly at first, learning how the cabin responds when a hand pushes off a panel. Every motion is a small lesson in momentum, because in microgravity, you do not stop unless you plan to stop. The cabin lighting shifts into a softer operational mode, and the spacecraft begins to feel like a place to live rather than a vehicle to survive. Suits are doffed carefully, because suit integrity is still a contingency, not a relic. The cabin is checked for leaks, humidity trends, and temperature stability across attitudes. A slow leak is not dramatic, but it is relentless, and it forces decisions about oxygen reserves and timeline. Fans and ducting must keep air mixed, because in microgravity, exhaled CO2 can linger near the face. The crew watches sensors not out of anxiety, but but out of respect for how quickly small imbalances can grow. ECLSS checks focus on CO2 removal, airflow distribution, and sensor agreement across redundant channels. Scrubbers are tested against expected metabolic loads, not just against nominal settings. Carbon dioxide is invisible, but it is physiologically loud because headaches and cognitive slowing arrive before panic. Redundancy matters because a single sensor can lie, and in deep space, you cannot afford to believe it blindly. The crew confirms that readings match across channels. Then they confirm that the system responds when they change cabin conditions. Water systems are verified for flow, taste, and microbial control assumptions. In a closed environment, water is both comfort and chemistry, and it must remain predictable. Filters, lines, and storage bladders are checked because biofilms can form where flow is slow. Waste management is validated early because small failures become large when days accumulate. There is no graceful way to ignore a hygiene problem in a sealed cabin, and discomfort can become distraction. The toilet is not a punchline in deep space. It is a cognitive load reducer. If basic functions fail, crew attention is stolen from navigation, power, and fault response. In spacecraft history, crews have endured improvised solutions, but endurance is not the same as capability. Artemis is trying to build a repeatable operating system, not a heroic anecdote. The better the basics work, the more mental bandwidth remains for the tasks that actually move the mission forward. Medical checks establish a baseline before radiation and sleep shifts can blur the picture. Heart rate, hydration, and motion sickness are tracked as operational variables. Space adaptation syndrome is not weakness, it is physiology responding to a new gravity vector. The crew logs symptoms and trends because the mission is also a data set meant to inform future flights. Sleep is treated as hardware because reaction time and judgment are as critical as valves and thrusters. Every checklist item is a reminder that deep space is not a destination. It is a living condition. The spacecraft is a habitat that must remain stable while the environment grows harsher. Even the smell of the cabin matters because it is a diagnostic clue as much as a comfort. The crew listens to fans, pumps, and valves, learning their normal tones. When a sound changes, it can be the first hint of a mechanical story beginning. Then comes a quiet rehearsal that reveals the program's deeper urgency. Orion performs proximity operations with the ICPS, treating a spent stage like a future docking partner. The ICPS is not designed as a station, yet it becomes a stand-in for the larger elements Artemis intends to assemble. This is a rehearsal in the most literal sense, repeating a motion now so it can be trusted later. The crew prepares for manual control, knowing that autonomy is powerful, but human judgment is still a tool. The crew takes manual control and uses RCS thrusters to adjust relative motion. The goal is not speed, it is precision and restraint, because propellant is time. Each thruster pulse is a tiny exchange, converting stored chemical energy into a change in velocity measured in centimeters per second. In orbit, those small changes accumulate into meaningful geometry, and that is why piloting is often about patience. The spacecraft does not glide like an airplane, it drifts, and then it obeys impulses with delayed, honest motion. Sensors fuse star tracker data, inertial measurements, and optical cues to build a coherent picture. Relative navigation is tested as a human-machine partnership, not as an autopilot trick. Cameras and LiDAR-like ranging concepts, along with line-of-sight angles, help estimate distance and closing rate. The crew cross-checks what the displays say against what the window shows because perception is part of the loop. It is a subtle test of trust. Trust in sensors, trust in algorithms, and trust in the crew's own interpretation. Orion approaches to roughly 9 meters and holds station without contact. At that distance, the other vehicle is close enough to feel present and far enough to be dangerous. Station keeping proves that the vehicle can stop drifting, even when small impulses accumulate. The thrusters fire in brief whispers, and the spacecraft responds with slow, deliberate translations. The background is a black field scattered with stars, and the target stage hangs against it like a piece of industrial sculpture. This is piloting under deep space constraints, where the ground cannot fly the spacecraft for you. It is also choreography, because future missions will require the same dance around larger, heavier targets. In the Artemis plan, docking is not an optional flourish, it is a structural requirement. You cannot land with one vehicle, return with another, and assemble them in lunar space without reliable proximity operations. The rehearsal is therefore both technical and philosophical, an admission that exploration now depends on coordination. Docking matters because Artemis is not one vehicle going to one place. Artemis is an architecture that depends on rendezvous with the human landing system and other cislunar elements. That word, architecture, signals a shift from the Apollo era when a single Saturn V carried nearly everything needed. Modern missions distribute mass and capability across multiple launches, which reduces single-point constraints but increases integration demands. The price of flexibility is choreography, and choreography must be proven. Without reliable rendezvous and docking, the Moon remains unreachable even with powerful rockets. The lander cannot be used if the crew cannot meet it, align with it, and transfer safely. Alignment is not only physical, it is also procedural, because hatches, pressure equalization, and power interfaces must be managed. A docking event is a chain of sensor readings, thruster decisions, and structural loads. If any link behaves unexpectedly, the mission must have a way to back out without damage. The proximity demo is therefore a dress rehearsal for an interplanetary transport system. The program is accelerating to validate this choreography before budgets and geopolitics reshape the cadence. Space exploration has always been shaped by politics, from Cold War urgency to modern coalition building. Artemis carries that history in its timelines and its partnerships, even when the cabin feels quiet. The crew's careful station-keeping becomes a small act with large implications, because it is proof that the architecture can be flown. After proximity operations, separation is executed cleanly, and the ICPS becomes background. Orion's focus returns to navigation solutions that will soon be measured in light seconds. The spacecraft drifts away, and the stage becomes another object in orbit, fading into the geometry of Earth. The crew returns to checklists that feel familiar, yet the context is changing. The mission is approaching the next commitment point, where going home stops being automatic. As the orbit arcs toward the planned burn, the mission's clock tightens again. Translunar injection is the moment where Earth stops being the default and becomes a reference point. The planned burn is a line in the timeline, but it is also a line in energy space. Engineers speak in delta V because velocity change is what buys new orbits. The crew watches the numbers, knowing that a correct burn is not just thrust, but thrust in the right direction for the right duration. The ESM main engine ignites for TLI with a burn that is long enough to feel like commitment. The push is steady, and the crew can sense the spacecraft's attitude holding firm against the thrust vector. Velocity increases until the trajectory's energy crosses the threshold for lunar transfer. The engine's performance is measured in chamber pressure, propellant flow, and acceleration, and each parameter must stay within a narrow band. Outside the window, Earth slides slowly, and the horizon line tilts as guidance maintains the planned attitude. Breaking Earth's grip is not about leaving the atmosphere, it is about changing orbital energy. The spacecraft moves from bound ellipse to a path that will not naturally return without intent. In plain terms, Orion is climbing out of a gravity well, exchanging engine work for altitude and speed relative to Earth. The math is classical, but the meaning is visceral, because the mission is now committed to a multi-day coast. The engine shuts down, and the spacecraft is suddenly weightless again. Yet it is weightless on a different kind of path. After shutdown, the crew confirms burn performance against predicted delta V and residuals. Small dispersions matter now, because small errors grow into large misses over distance. Guidance filters compare expected velocity change to measured change, and they compute how the trajectory will evolve. If the burn is slightly short or slightly long, the correction is possible, but it consumes propellant and planning attention. The crew and ground teams share a quiet relief when the numbers converge, because convergence means the mission is still on the intended rail. Orion begins outbound coast, and Earth starts shrinking into a single object. The psychological distance increases before the physical distance feels real. At first, Earth is still huge, filling the window with blues and whites, and it is hard to believe it will become small. Then, hour by hour, it becomes a disk, and then a bright sphere, and then a landmark. The spacecraft's interior remains the same size, which makes the outside change feel even more profound. Communications remain strong at first, then latency begins to appear as a subtle delay. The voice loop gains a fraction of a second, then seconds, and conversation changes shape. People stop interrupting, not out of politeness, but because the physics of light demands it. That delay is not inconvenience, it is a preview of autonomy requirements. When the spacecraft is far enough, the crew must act before Earth can answer. Navigation geometry also changes as Earth-based tracking angles narrow and star fields dominate. The spacecraft relies more on onboard state estimation and optical navigation cues. Star trackers identify patterns and lock onto reference stars, turning the sky into a coordinate system. Optical navigation can use images of Earth and the Moon against star backgrounds, measuring angles that become position estimates. These methods are elegant because they use what is already there, light and geometry, rather than requiring constant thrust. Outbound correction burns arrive as tiny impulses that steer a 250,000-mile trajectory. They look gentle, yet they encode modern exploration's core skill, precision over brute force. A correction burn is planned, executed, and verified with careful bookkeeping of propellant and attitude. Each impulse is a choice that trades fuel for certainty. The crew watches the thruster firings on displays, and they feel almost nothing, yet the trajectory changes in a way that will matter days later. In a sense, these burns are the opposite of launch, where everything is loud and immediate. Here, the spacecraft is a quiet instrument, and the mission is a long calculation performed in real time. The smallest errors are still errors, and deep space is patient enough to let them grow. That is why verification is not bureaucracy, it is survival logic. When you are far from Earth, you cannot afford to discover a mistake only when it becomes visible. Radiation awareness becomes more than a briefing as Orion departs the magnetosphere's strongest protection. Dosimeters track cumulative dose, while space weather forecasts become daily context. Radiation is not one thing, but a mixture of particle populations with different energies and behaviors. Galactic cosmic rays form a steady background that cannot be weighted out. Solar particle events remain the spike risk, demanding procedures for sheltering and power management. The crew reviews storm shelter concepts and verifies where mass provides the best shielding. Water, supplies, and equipment placement become part of radiation strategy, not just stowage. The idea is simple in plain language. Put dense material between you and the particles, but the execution is constrained by volume and accessibility. The crew needs to reach shelter quickly if an alert arrives, and they need to keep critical systems running while they do. Even the act of stowing bags becomes a quiet form of engineering, because placement can change exposure. Deep space rhythm settles in as days become structured by checks and sleep cycles. Medical monitoring continues because cognition is a safety system and sleep debt erodes it. The crew's days are not empty, they are filled with small confirmations that keep the habitat stable. They log temperatures, pressures, and consumables, and they compare trends against expected curves. In the background, the spacecraft's power system balances generation and load, because energy is another consumable with its own margins. Suit integrity remains relevant even without launch loads, because a leak is always possible. The crew practices response steps that must be executed without panic and without delay. Emergency procedures are rehearsed until they become muscle memory, because stress narrows attention. A cabin leak would be detected by pressure trends, but the response requires coordinated action: locate, isolate, and stabilize. The crew treats these possibilities as real, not because they expect failure, but because readiness is the price of survival. The cabin sounds become familiar, and that familiarity can be dangerous. Complacency is a human failure mode, so procedures keep attention anchored to measurable trends. A fan that changes pitch, a pump that cycles differently, or a sensor that drifts can be the first hint of a larger issue. The crew learns to notice without catastrophizing, which is a skill as technical as navigation. Deep space does not reward panic, but it also does not forgive neglect. Outside, Earth's magnetic cradle is no longer assumed, and micrometeoroids become baseline risk. The spacecraft's shielding and Whipple layers are passive, but the awareness is active. A micrometeoroid impact is unlikely, yet the consequences can be sharp, especially for radiators, windows, and thin structures. The crew cannot see these particles, but they can see the emptiness that carries them. The view is stark: black space, hard sunlight, and a few bright objects that feel suddenly precious. The mission's mysterious undertone sharpens here, because the universe feels more honest. The crew is still close enough to see Earth clearly, yet far enough to feel how exposed it is. Earth becomes a bright, fragile sphere, and the atmosphere becomes a thin halo that looks almost painted on. The spacecraft is a small, moving island, and everything it needs is inside its walls. That contrast raises a quiet question: how much of our confidence has always depended on being able to go back quickly? Artemis II's race is not toward a flag moment, it is toward a validated operating system. The mission is proving that humans can manage life support, navigation, and rendezvous while leaving Earth's protective context. It is also proving that procedures remain coherent when the environment becomes less forgiving. The crew's work is methodical, not cinematic, and that is the point. A sustainable presence beyond Earth will be built from repeatable days, not singular heroics. As the outbound coast continues, the Moon stops being a symbol and becomes a target with gravity. Its position is tracked as a moving solution, not a fixed landmark. Approach is measured in changing relative velocity and changing light, not in romance. The Moon's surface texture begins to resolve, and craters become more than patterns. The crew watches predicted flyby parameters tighten as navigation updates converge, because convergence means the trajectory is behaving. Then an invisible border arrives, and it has nothing to do with maps. Orion crosses into the Moon's gravitational sphere of influence, where lunar gravity becomes the dominant guide. The transition is mathematical, yet it feels like entering another world's domain. Earth is still present in the sky, but the trajectory now belongs to the Moon. In practical terms, the guidance team begins thinking in lunar-centered frames, because the Moon is now the primary attractor shaping the path. This sets up the far side passage and the coming blackout behind the lunar limb. The next phase will test autonomy, timing, and trust when Earth cannot speak back. The crew reviews timelines with extra care because a missed action during blackout cannot be corrected by a quick call. The spacecraft's clocks, stored commands, and onboard fault protection become the mission's voice for a while. Silence is not emptiness here. It is a planned condition that must be managed. The clock keeps running, and the distance keeps teaching, because the space between worlds is the real subject. Artemis II is racing to prove we can survive that space before the universe forces the lesson harder. Each day outward is both a technical demonstration and a human one, showing whether discipline can outlast novelty. The spacecraft continues on, steady and small, carrying its fragile atmosphere through a region that offers no forgiveness and no pause. Day 6 begins with a quiet truth, spoken more by instruments than by voices. The mission's peak danger is not impact or explosion, it is isolation at maximum distance. when help becomes geometry and time becomes a fixed cost. Orion is not aiming to break into lunar orbit, and that choice is deliberate. It is threading a free return trajectory designed to come home even after failures. The path is a loop written into gravity, not a promise written into schedules. A free return arc is sometimes described like a safety net, but it is stricter than that metaphor. It is a corridor of timing and velocity that must be entered precisely. Miss the corridor, and the moon does not save you. It misdirects you. In practical terms, the corridor is defined by the spacecraft's position and velocity vector at a specific time. Navigation teams call it a state vector, but the crew feels it as a narrowing funnel. Every hour of coast makes the funnel tighter, and every correction, burn earlier, was buying this moment. The crew reviews the flyby timeline as a chain of irreversible minutes, because some events cannot be rescheduled. Attitude targets matter because antennas and thermal control must agree. Power budgets matter because eclipse and camera use can shift loads, and those shifts ripple through everything. Inside Orion, the displays make the abstract visible in small, relentless numbers. Range to the moon ticks down, while predicted closest approach stabilizes to the second. Star trackers and inertial measurement units keep the spacecraft oriented, and the crew watches for any drift that could compound. Outside the windows, the moon grows from a target into a horizon, and then into a wall. What was once a flat disk becomes a sphere with curvature and depth. Navigation updates tighten, and the state vector stops being a concept and becomes a place. The flyby is a gravity assist in its simplest form, but simple hides the precision. The moon's mass bends Orion's velocity vector, trading direction for a small change in speed. The spacecraft falls toward the moon and leaves with its path rotated toward Earth. That bend is the real engine of the return, and it does not burn propellant. Gravity assist works because momentum is redirected in a moving gravitational field, and the moon's pull reshapes the trajectory. The effect looks gentle on plots, yet it is decisive in space. The crew can feel none of this physically because freefall erases sensation. The only clues are the changing angles in the guidance pages and the slow sweep of the lunar limb. In microgravity, the most dramatic forces announce themselves as geometry. This is why Apollo 13 could come home without a main engine. Artemis II uses the same physics intentionally, turning a past emergency into a planned architecture. A crisis once forced the technique, and now the technique is tested as a repeatable method. The central question sharpens here as the moon fills the frame and the stakes feel older than the spacecraft. Why race to the moon now if the moon is not the destination? Because the space between worlds is the test, and the return loop must be proven repeatable. A loop is not just a path through space, it is a claim about reliability. It says that a crew can be sent outward and still be brought back under degraded conditions. It is the scaffolding for future missions that cannot depend on perfect days. As Orion approaches closest passage, the mission reaches its psychological milestone. The distance surpasses Apollo 13's record, and the number becomes a story. The crew passes 252,760 miles from Earth, farther than any humans have traveled. That record is not a stunt metric, and the program treats it like more than a headline. It is a cognitive threshold that changes how the crew thinks about home. Beyond that number, Earth is not a place you can reach quickly, it is a place you must earn. From this far away, Earth's light is steady and small, like a bright bead pinned to velvet. Continents are no longer readable, and weather is only a suggestion. The planet is reduced to a sphere with a thin, pale rim that looks too delicate to be real. Historically, the record matters because it reopens a closed era. Apollo's farthest point became a memorial to risk and improvisation. Artemis turns that farthest point into a controlled experiment with modern instrumentation, modern telemetry, and modern expectations. The Apollo 13 record was achieved under damage, smoke, and limited power, with a crew improvising to survive. Artemis II reaches beyond it with intention, and that difference is the point. The question is whether deep space can be normalized without losing respect for it. The moon's near side is familiar in maps, but the far side is still psychologically charged. The phrase "dark side" persists, as if the moon hides in permanent night. The mission has to correct that myth without losing the mystery that made it stick. The far side is not permanently dark, and it never has been. Sunlight reaches it as predictably as it reaches the near side, because the moon rotates once per orbit. It is dark to radio because the moon blocks line of sight to Earth. That is the real meaning of the coming silence, and it is almost disappointingly physical. Communications do not fail because hardware breaks. Communications fail because a sphere of rock becomes a shield between antennas, and the laws of propagation do not negotiate. As Orion slips behind the lunar limb, the signal drops on schedule, and the timing is almost theatrical. The voice loop ends in mid-thought, and the world becomes local. For roughly 40 minutes, there is no conversation with Earth. This is the mission's most absolute isolation, because it is planned and still unsettling. The crew cannot ask for confirmation, and the ground cannot correct a mistake. Autonomy is not a feature here, it is the only mode. The tension is built through what does not happen, and that absence becomes a kind of soundtrack. No new instructions arrive, and no reassurance returns. The spacecraft's clocks and fault protection become the mission's only external authority. In mission control, the silence has its own choreography. Controllers stare at predicted timelines, watching for the moment the carrier should return. They cannot see Orion, and they cannot hear it, so they lean on models and trust the math. Inside the cabin, procedures compress into essentials, and the crew's voices become quieter. They monitor attitude, thermal trends, and consumables. They confirm that the free return geometry remains intact without outside validation, because the numbers must be self-consistent. Attitude control is not just about pointing cameras, and the crew treats it like life support. If the spacecraft drifts, antennas can lose their future link, and radiators can warm. Even sunlight on the wrong surface can change thermal balance over hours. The blackout also reframes the earlier theme of exposure, because it removes the last illusion of connection. Outside Earth's magnetosphere, radiation is baseline physics. Behind the moon, even radio is denied, and the universe feels more indifferent. Yet the blackout is also a scientific window, because the far side is briefly the cruise alone. The far side passes beneath Orion at about 4,066 miles altitude. That distance is high enough for broad context, and close enough for human eyes to notice lighting subtleties. The surface below is not uniformly grey when the sun hits it at an angle. Shadows pool in crater rims, while highlands brighten in a chalky sheen. Mare regions, darker and smoother, look like cooled ink spilled across older terrain. Robotic imaging has mapped the moon in detail, but humans bring a different instrument. The crew can integrate contrast, texture, and shadow in real time, while their brains automatically compare features across a wide field. They can spot relationships between features that algorithms might not prioritize. Phase angle becomes the hidden variable, and the crew knows to respect it. Under specific lighting, shallow relief becomes visible, and older structures reveal their rings. Their observations are tied to geometry, not romance, because geometry decides what can be seen. At low sun angles, the moon behaves like a relief map, and the smallest ridges cast long shadows. At high sun angles, the same ridges vanish into glare, and only albedo differences remain. The crew watches these changes unfold as the spacecraft's viewpoint shifts. The mission's geological focus centers on the Oriental Basin, a scar with unusually clear architecture. It is a multi-ring impact structure, one of the youngest large basins on the moon. Its age is about 3.8 billion years, near the era of heavy bombardment. Oriental matters because it is a preserved record of early solar system violence, not a metaphorical one. Its rings and ejecta patterns record how crust responds to enormous impacts. It is a natural experiment that cannot be rebuilt on Earth, because Earth erases its own oldest wounds. The basin's rings are not just circles. They are evidence of mechanical failure in a planetary crust. When an impact excavates deep material, the crust rebounds and collapses in stages. Those stages can freeze into concentric structures that reveal strength, layering, and fracture behavior. Ejecta rays extend outward like frozen shock waves, and their brightness hints at composition and maturity. Fresher material reflects sunlight differently because micrometeorite gardening has not yet darkened it. The crew notes where rays cross older terrain, because overlap tells relative age. The crew's job is not to replace orbiters, and they do not pretend otherwise. It is to add context that orbiters cannot easily capture under the same lighting and time constraints. They note ring boundaries, ray patterns, and subtle albedo changes that hint at composition. They also note the way features connect across scales, from basin-wide rings down to clustered craters. A camera can record pixels, but a human can recognize a pattern and ask why it repeats. That why becomes a prompt for later analysis on the ground. These observations feed the larger Artemis rationale, which is broader than a single flight. The Moon is an archive of impacts that Earth has erased through weather and plate tectonics. Reading that archive helps quantify how hazardous the early neighborhood was and how often worlds are reset. The hazard is not only ancient, and the narration does not let it stay safely in the past. The same physics that created the Moon still operates, just less frequently. Artemis is racing because the universe's violence is not a metaphor. It is a background rate. When a rock strikes the Moon, the evidence remains for billions of years because there is no rain to soften it. On Earth, the same strike can be swallowed by erosion, buried by sediment, or recycled by plate boundaries. The Moon keeps receipts that Earth throws away. During the far side pass, another alignment arrives as a quiet spectacle, and the crew notices it with a kind of reverence. From deep space, the Sun can be eclipsed by the Moon in a way Earth rarely allows. The corona becomes visible when the disk is perfectly covered. The eclipse is not a postcard moment, it is orbital geometry made visible. It shows how precise the flyby alignment is and how small changes would break it. The crew watches a cosmic clockwork that does not care who is watching. In the window, the sun's glare collapses into a thin ring, and the cabin light changes instantly. The corona appears as a faint, textured halo, delicate and uneven, like breath on glass. It is a reminder that the sun is a physical object with structure, not just brightness. The crew knows that eclipses are also data, because they reveal scattering and exposure behavior in cameras. They watch for lens artifacts, sensor saturation, and the way the scene's contrast challenges dynamic range. Even beauty becomes a test of documentation. Then the blackout ends as abruptly as it began, and the return of signal feels like a door opening. Orion clears the limb, and the carrier signal returns. Earth hears the crew again, and the relief is immediate, even in controlled voices. With comm restored, the mission shares its most public images, and the timing is not accidental. Earthrise appears again, but now with modern bandwidth and modern expectation. Orion to Orion streaming in 4K changes how the public feels distance, because distance becomes visible detail. Bandwidth is not just outreach, and the program treats it as part of the mission's instrumentation. Higher resolution preserves scientific documentation of lighting and horizon geometry. It also makes the psychological thesis legible, because Earth's thin atmosphere becomes visible as a boundary. In 4K, the atmosphere is not a vague glow, it is a fragile line that can be traced. The limb shows a gradient from deep blue to black, and the transition is fast. The image quietly asks how much protection that line really provides. Earthrise in 4K becomes a modern echo of Apollo 8, but the echo carries different weight. The earlier image changed how humans imagined home. This version changes how humans measure vulnerability. because the planet looks smaller and more isolated. The camera also captures the moon's foreground in sharper texture, and the contrast matters. Crater rims look like torn paper, and the regolith appears powdery and old. The scene is a layered composition. Ancient rock below, living world above, and silence between. The narrative pivot begins here. The flyby is the outward climax, but the return is the real verdict. The mission shifts from wonder to discipline, because the ship must close the loop. Day 7 is a coast day shaped by checklists and contingencies, and the pacing becomes intentionally methodical. The crew reviews radiation procedures with a seriousness that is not performative. Solar particle events are rare, but the response must be immediate, because warning time can be short. Radiation in deep space is not one thing, and the crew is trained to distinguish it. Galactic cosmic rays are a constant drizzle of high-energy particles, difficult to shield completely. Solar particle events are bursts, sometimes intense, and they demand a rapid change in posture and shielding. Dosimeters log cumulative exposure, but they also track rate, because rate changes the decision. A slow accumulation is managed over days, while a spike demands shelter. The crew reads these numbers like weather, because in deep space the weather is invisible. They conduct a radiation shelter drill in the cabin's best shielded volume, and the drill is deliberately physical. Water bags, food, and stowed equipment become shielding mass. The crew practices building a barrier quickly, because mass between body and particles is the simplest defense. The shelter is not a bunker, and no one pretends it makes them invulnerable. It is a way to reduce dose during the worst hours, when energetic protons would otherwise pass through tissue. The plain language goal is simple: take less damage while you wait. This is human performance as an engineering variable, and the program measures it that way. The shelter plan is only real if it can be executed while stressed and fatigued. Artemis is not only testing hardware, it is testing whether procedures survive reality. Fatigue changes everything in a sealed cabin, because small errors can cascade. A missed latch can become a floating hazard, and a misread display can become a wrong configuration. The crew's training is meant to make the right actions automatic, even when attention narrows. Waste management becomes part of the same theme, because it is not glamorous, but it is constant. Backups are verified because small hygiene failures can cascade into distraction. In a sealed cabin, discomfort is not private, it is operational. The systems are designed to contain odor, moisture, and microbial growth, but design is not the same as use. The crew checks seals, airflow paths, and storage capacity, because a minor leak can become a persistent stressor. Deep space does not forgive slow problems that grow quietly. The crew also tests manual piloting again, now in a different context, because context changes workload. They evaluate handling qualities, display logic, and thruster response. The goal is to prove that humans can take over when automation is uncertain, without introducing new risk. Manual control in space is not like flying in air, and the crew knows that instinct can mislead. There is no continuous lift, and there is no aerodynamic feedback. A small thruster pulse changes rotation, and that rotation persists until countered, like a thought that keeps spinning. They watch propellant usage during these tests, because propellant is both control authority and contingency margin. Every pulse is a trade, and the trade must be justified. The crew learns how the spacecraft feels through numbers, not through pressure on a yoke. Compression garments enter the story as a quiet countermeasure, and the reason is physiological. Re-entry loads will be higher under a ballistic profile. The crew prepares their bodies for G-forces that will arrive after days of microgravity deconditioning, when blood distribution has changed. Microgravity shifts fluids toward the head, and over time the body adapts by reducing plasma volume. That adaptation is useful in space, but it becomes a liability during high G. Compression helps keep blood from pooling, reducing the risk of lightheadedness when gravity returns abruptly. Day 8 continues the return coast, and the mission's distance begins shrinking in a way that feels like reversal. Earth grows from a bright star into a disk again. The psychological arc turns back toward home, but the risk does not relax, because the hardest physics is still ahead. The spacecraft remains outside Earth's magnetic cradle for most of the coast, and that absence is measurable. Dosimeters continue logging cumulative exposure, and the crew's sleep and cognition are tracked because judgment is a consumable. A tired mind can mishandle a checklist as easily as a tool. The crew's schedule balances work and recovery because performance is not linear. Short sleep can degrade reaction time and memory, and those are entry-critical skills. The mission treats rest as a system requirement, not a luxury. This is where the program's race becomes clearer, and it is not a race for spectacle. Artemis is racing to prove that deep space days can be routine. Routine is the foundation of infrastructure, and infrastructure is the only path beyond one-off heroics. A routine mission still requires respect, but it cannot require improvisation as a default. The goal is repeatability. Predictable consumables, predictable timelines, predictable recovery. Each normal day on the return coast is a small argument that the system can scale. Day 9 brings entry preparation, and the earlier heat shield mystery returns with a sharper edge. Chapter 4 raised the question of avcoat cavities and spalling risk. Now the mission must live inside the chosen mitigation because the atmosphere will not accept excuses. Avcoat is an ablative material, which means it protects by sacrificing itself. As it heats, it chars and decomposes, and gases vent outward through the material. That venting carries heat away, while the char layer insulates what lies beneath, but only if the material stays cohesive. The mitigation is not a new material, it is a new way of meeting the air. Artemis II commits to a single-pulse ballistic re-entry, avoiding skip entry's longer thermal soak. The bet is that shorter exposure reduces internal overpressure risk, even if peak loads are higher. The crew reviews the entry corridor as a narrow, three-dimensional gate, and the visuals are unforgiving. Too steep and heating, and G-loads spike beyond limits. Too shallow, and the capsule skips out, forcing a second entry with uncertain heating history. The corridor is a geometry problem that becomes a survival problem, and the crew treats it with quiet intensity. Guidance must hit a precise flight path angle at interface. Small navigation errors are amplified by hypersonic aerodynamics because air becomes a force multiplier at speed. Service module separation is the last clean mechanical boundary before the atmosphere, and it carries both risk and finality. The European-built module has carried power, propulsion, and life support. It is discarded because it cannot survive entry and because mass must be minimized. Separation is both routine and symbolic, and the camera would linger if it could. The crew module becomes a self-contained seed again, like Apollo. The architecture falls away until only the heat shield and pressure vessel remain, and the ship becomes simple in the most serious way. Small thrusters orient the capsule for entry, and the attitude matters immediately. The heat shield must face forward, and the lift vector must be controlled for corridor targeting. Even in a ballistic profile, the capsule's orientation shapes how it rides the shock and distributes heat. Entry interface arrives at roughly 25,000 miles per hour, and the atmosphere is thin at first. Then it quickly becomes a compressible wall. Kinetic energy begins converting into heat, and the plasma sheath forms as air molecules dissociate and ionize under shock heating. The radio blackout returns, but now it is caused by ionized air around the capsule. The earlier lunar blackout was geometry. This blackout is chemistry and electromagnetism, a different kind of silence, because the plasma can absorb or refract radio waves. Inside, the crew feels the onset of deceleration, and the change is unmistakable. The ballistic profile concentrates the event into one main pulse. The G-load rises, and the cabin becomes heavy again, as if gravity is being switched back on in stages. Breathing becomes more deliberate under load, and voices tighten without drama. The crew's training includes how to speak and act when weight multiplies, because fine motor control changes. Checklists are designed for this moment, when cognition must remain organized. The heat shield is now the mission's quiet protagonist, and the narration stays close to its behavior. Avcoat ablates, chars, and vents pyrolysis gases as designed. The question is whether it does so without chunk loss that would expose structure, because exposure would change heating rapidly. Sensors record temperatures, pressures, and structural response, turning the shield into data as well as protection. The program will compare these traces to models, looking for surprises. A heat shield is judged not by how it looks in theory, but by what it endures in flight. The documentary holds the tension without pretending certainty, because uncertainty is part of engineering honesty. The root cause of Artemis I's cavities may never feel emotionally closed. Flight data and post-recovery inspection will be the only final argument, and the ocean will not soften the verdict. Peak heating passes, and the capsule descends into thicker air, where control changes character. Plasma fades, and communications return. The crew's voices are back, but the mission is not finished, because descent is a sequence of mechanical commitments. Drogue parachutes deploy first, stabilizing the capsule and reducing speed, and the event is violent in its own way. The lines snap taut, and the capsule's motion damps. Then the main parachutes blossom in sequence, each one a structural event with its own failure modes. The canopy loads must be symmetric enough to avoid oscillation, and the system is designed with redundancy. Reefing stages control how quickly the chutes inflate, preventing a single shock from tearing fabric. The crew feels the jerks as punctuation marks, each one meaning the system is working. The final descent is slow enough to feel calm, but it is still physics, and physics is not sentimental. Wind, sea state, and capsule attitude determine the impact. The crew braces for splashdown as the ocean becomes the last interface, dark and textured beneath them. Splashdown in the Pacific is the end of the loop, and the moment is both ordinary and historic. Recovery forces move in with practiced choreography. The USS Somerset approaches, and divers secure the capsule for hoist and crew extraction, treating it like both vehicle and evidence. The recovery is not epilogue, it is part of the architecture, and the program frames it that way. A repeatable cadence requires repeatable retrieval, inspection, and refurbishment. The capsule's condition will shape the next mission's confidence, because hardware tells the truth about margins. On deck, the capsule is surrounded by people in helmets and vests, and the scene looks almost industrial. Salt water drips from scorched surfaces, and the heat shield's char is visible in daylight. The spacecraft that looked pristine in space now looks used, and that is the point. As the crew is brought aboard, the chapter resolves its central mystery with a restrained clarity. Artemis II went behind the moon and returned through plasma. It proved that isolation can be planned and that return can be engineered if the geometry is respected and the procedures hold. The chapter ends with a forward pull because the loop is not an ending. The mission has not landed on the moon, yet it has changed what the moon means. It has shown the nearest archive of cosmic violence and the first working loop beyond Earth's shield. Transition to Chapter 7. The question becomes what this loop enables next, and what it demands from a species that is still learning to live between worlds. The flyby proved the loop can close. Chapter 7 asks what the loop unlocks, and why the program is moving faster than comfort. Artemis II is racing because it is a gating mission for an architecture, not a single destination. If humans cannot live, navigate, communicate, dock, and return reliably, nothing else scales. The point is not the photograph of Earth shrinking behind a window. The point is whether the entire chain behaves like an operating system, with predictable inputs and bounded failure modes. Daily life on board becomes deep space systems engineering, because biology is the payload and the constraint. In microgravity, even simple actions reveal hidden couplings. Airflow, moisture, particulates, and crew time all interact. A floating crumb is not just a nuisance, It is a filter load and a contamination pathway. A mist wipe-down is not just untidiness, it is microbial ecology inside a sealed habitat. Visually, the cabin looks calm, but it is dense with invisible motion. Fans push air through ducts, so exhaled carbon dioxide does not pool in pockets. Velcro, tethers, and labeled bags turn three-dimensional drift into a controlled workspace. Every handhold is a design decision, because a body without weight still has momentum. Sleep is scheduled like propellant, because fatigue is a hidden loss of crew pathway. Circadian drift, workload peaks, and comm delays force a new discipline that Apollo rarely required. In low Earth orbit, the station can cool down specialists in minutes, and the crew can borrow time from tomorrow. In cis-lunar space, tomorrow may arrive with a communications gap, and the body will still demand recovery. Light becomes a tool rather than a backdrop. Blue-enriched illumination can push alertness, while warmer tones can help the brain downshift toward rest. Temperature, noise, and even the timing of meals can nudge a circadian rhythm that no longer has sunrise and sunset. The question is blunt. How do you keep judgment sharp when the environment refuses to anchor time? Actigraphy tools like Arca turn rest into data, not self-report. The program needs objective sleep and activity traces to link performance to radiation and stress. A wrist-worn sensor can capture motion patterns, micro-awakenings, and the fragmentation that people often forget by morning. Those traces can be compared against cognitive tasks, reaction times, and mood check-ins. The goal is a predictive relationship, not a post-mission story. Exercise is not about fitness optics. It is about keeping a body functional for entry and future landings. Bone resorption accelerates in microgravity, and muscles that stabilize posture lose load almost instantly. Fluids shift toward the head, which can change vision and intracranial pressure over time. Even a short mission is an opportunity to validate countermeasures, because the physics starts working on the body immediately. The compact FED device matters, because it uses no power and little volume. It is a small object with an outsized implication, because it treats exercise as a mechanical requirement. Elastic resistance can load major muscle groups without a treadmill's mass or a cycle's electrical draw. The crew can anchor it to the vehicle's structure and create repeatable force profiles. In the visuals, the motion is quiet and controlled, straps taut, breath audible, sweat suspended in tiny spheres. That design choice is a quiet admission about deep space. Power margins will be fought over by comm, thermal control, and life support, not by comfort. Batteries and solar arrays are not abstract numbers. They are a budget with competing claimants. A high-gain antenna wants watts, a heater wants watts, and a CO2 scrubber wants watts. Every additional load is a negotiation with risk. Waste management is treated as mission critical because distraction is risk. The UWMS toilet is not a luxury upgrade, it is cognitive bandwidth protection. If a system is unreliable, it steals attention from navigation, procedures, and anomaly response. The hardware must manage airflow, separation, and containment in a place where gravity cannot help. In a sealed cabin, odor control is not vanity, it is crew performance. The visuals here are unglamorous, and that is the point. A checklist is taped near the unit, and a small kit of wipes, bags, and tools sits within reach. A fan's hum becomes part of the habitat's soundscape, because airflow is the substitute for down. The crew learns quickly that hygiene is not a private routine. It is a shared systems interface. Food is also engineering, because packaging, crumbs, and shelf life become hazards. Constraints on mass, water, sodium, and variety shape morale and metabolism together. Meals must survive vibration, radiation, and months of storage without refrigeration. The packaging must open cleanly, because fragments can migrate into vents and connectors. The menu must also respect physiology, because sodium affects fluid balance and bone health. The food system is a rehearsal for longer missions, where resupply is not a calendar event. Every menu choice becomes an input to waste streams, water budgets, and medical outcomes. A pouch that requires rehydration trades mass for water demand. A high-fiber option changes digestion, which changes waste handling and crew comfort. The crew's feedback is not culinary critique, it is operational data. ECLSS performance is validated in the only place that matters, inside a crewed pressure vessel beyond Earth's shield. CO2 removal, humidity control, and microbial risk are treated as coupled problems. When humidity rises, condensation can form in hidden corners, and microbes can exploit that moisture. When CO2 rises, cognition can degrade subtly, even before alarms trigger. The system must keep the cabin stable while the crew produces heat, water vapor, and carbon dioxide continuously. This is where earlier risk threads converge without drama. A motor controller anomaly, a sensor drift, or a leak becomes dangerous when fatigue and distance remove easy recovery. In Earth orbit, a spare can be launched, and a specialist can talk a crew through repairs in real time. In cislunar space, the crew becomes the specialist, and the timeline becomes less forgiving. The vehicle must be designed so that failures fail slowly, and so that the crew can diagnose without guesswork. Artemis II's urgency is partly political, but the deeper driver is architectural fragility. The program must prove a repeatable operating system before norms and routes harden without it. History shows that early standards can become permanent even when they are imperfect. The first workable interface often becomes the default interface because changing it later is expensive. Artemis II is trying to set those defaults with evidence, not momentum. Communications are not just a voice loop. They are the nervous system of cislunar work. Latency, handovers, and blackout procedures become training for operations that cannot rely on constant ground control. Even a few seconds of delay changes how people talk, how they confirm steps, and how they handle uncertainty. The crew must learn to bundle information, to anticipate questions, and to act with partial oversight. That is not a stylistic change, it is a safety posture. The far side is the first rehearsal for a future where the moon blocks Earth by default. If you want science and industry there, you need relay networks and operational doctrine. Behind the moon, the radio goes quiet, and the silence is absolute. The visuals can linger on a slow rotation, Earth sliding out of view like a dimming lamp. In that moment, autonomy stops being aspirational and becomes mandatory. The phrase dark side persists because it describes radio, not sunlight. Artemis uses that myth as a teaching tool, then replaces it with infrastructure requirements. The far side receives sunlight, but it does not receive direct Earth contact. That distinction matters because it reframes romance into engineering. What looks mysterious from Earth becomes a problem of geometry, orbits, and antennas. A relay architecture turns isolation into a managed condition. It enables far-side astronomy, resource scouting, and robotic work that can be supervised with predictable links. A spacecraft at a stable vantage point can see both Earth and the far side, acting like a translator between worlds. That relay can carry telemetry, video, and command sequences, and it can enforce time discipline. When the link is scheduled, operations become schedulable, and schedulable operations become scalable. Artemis II also races because radiation is not a future problem, it is a present baseline. Beyond the magnetosphere, galactic cosmic rays become chronic, and solar storms become acute. Galactic cosmic rays are high-energy particles from distant events, and they arrive with relentless regularity. Solar particle events are rarer, but they can spike dose rapidly, and they can overwhelm a crew without warning. Dosimeters measure exposure, but the mission's real goal is a model that predicts risk. NASA needs dose, timing, shielding geometry, and biological response tied together. A badge can tell you what happened, but a model can tell you what to do next. Shielding effectiveness depends on thickness, material, and where the body is located inside the vehicle. Even water, food, and stowed equipment can become improvised shielding if the geometry is understood. Avatar organ-on-a-chip experiments push that link into tissue-level evidence. They test how radiation and microgravity alter organs, not just how they alter a badge. Tiny channels lined with living cells can mimic aspects of blood flow and organ function. When radiation hits, the response can be measured in inflammation markers, barrier integrity, and cellular stress pathways. It is a small experiment with a large purpose, translating physics into physiology. Immune biomarkers add another layer, because infection risk changes when immunity shifts. A Mars-class mission cannot treat immune suppression as an anecdote. Stress hormones, disrupted sleep, and microgravity can alter immune cell behavior. Latent viruses can reactivate, and wound healing can change. The program needs to know whether a crew becomes more vulnerable, and if so, when and why. ARCA actigraphy and cognitive measures connect sleep to immune response and decision quality. The program is building a data-driven shield because aluminium alone cannot stop high-energy particles. If sleep debt amplifies inflammation, then sleep becomes a countermeasure. If workload peaks correlate with errors, then scheduling becomes a form of shielding. The shield is partly material and partly operational design. This is the cosmology of survival. The universe does not target humans, but it constantly produces particles and impacts that make biology expensive. The same processes that build elements in stars also fling charged particles across space. The same gravitational dynamics that shaped planets also left debris on intersecting paths. The question is not whether hazards exist, but whether systems can make them tolerable. The Moon's surface is the nearest ledger of that violence. Craters persist because there is no weather, no oceans, and no plate tectonics to erase them. Each basin is a frozen event, a record of energy released in seconds. Rays of ejecta can remain visible for millions of years, like chalk marks on dark stone. From orbit, the terrain looks like hammered metal, bright rims and shadowed bowls repeating to the horizon. Earth looks safer partly because it deletes its own scars. Erosion and recycling hide the early solar system's impact history, and that makes hazard feel abstract. Oceans swallow craters, and continents reshape under tectonic stress. The atmosphere also acts as a filter, burning up small debris before it reaches the ground. We live inside a protective machine that we rarely notice. Returning to the Moon is also returning to evidence. The crater record is a timeline of bombardment that brackets when worlds were repeatedly sterilized or reshaped. By counting craters and dating samples, scientists infer when impacts were common and when they waned. That timeline informs how early environments evolved, including Earth's. It also reframes impacts as a continuing process, not a closed chapter. That record reframes Earth as an oasis with active defenses. The atmosphere burns up small debris, and the magnetic field deflects much of the charged particle flux. The magnetosphere channels particles toward the poles, where auroras glow like visible mathematics. It is beautiful, but it is also a warning sign that energy is being redirected. Without that field, the same particles would penetrate deeper into the atmosphere and into living tissue. Those defenses are not permanent guarantees. Magnetic fields wander, atmospheres change, and large impacts ignore both, which is why the Moon's archive matters. Geological history shows reversals and fluctuations in field strength. Climate history shows that atmospheres can thicken or thin over time. The Moon sits nearby, holding a baseline record of what happens without active recycling. Artemis II turns cosmology into engineering requirements. If Earth's protection is contingent, then off-world survival demands human-made equivalents. Some equivalents are physical, like shielding and storm shelters. Others are procedural, like warning networks, safe haven rules, and interoperable docking standards. The aim is to replace luck with design margins. This is where the Artemis Accords stop being paperwork and become survival governance. Safety zones, coordination, and resource norms reduce conflict where rescue is hard. In a place with limited bandwidth and limited redundancy, misunderstandings can become hazards. Shared expectations can prevent interference, and they can clarify responsibility when something goes wrong. Governance becomes another layer of life support. The race is also about default setting. If one coalition builds the first working logistics chain, its interfaces become the language everyone else must speak. The first refueling standard, the first docking adapter, and the first COM protocol can become hard to dislodge. History in aviation and computing shows how early choices persist. Artemis II is trying to ensure those early choices are safe, testable, and open to verification. China's ILRS timeline adds pressure, but the deeper competition is for standards that outlive administrations. Lunar space will reward whoever makes operations boring first. Boring here means predictable, auditable, and repeatable under stress. It means that a docking is routine, a COM handover is routine, and a life support maintenance cycle is routine. The prize is not drama, it is reliability. Artemis II validates the end-to-end chain that makes boring possible. Launch, deep space life support, navigation, COM, autonomy, and re-entry must all work together. Navigation is not only about where you are, but about how confidently you know it. Star trackers, inertial units, and radio ranging must agree within tight bounds. When they disagree, the crew and ground must have a method to reconcile reality. The mission is a systems integration exam, not a sightseeing tour. Passing it means later missions can focus on building, not merely surviving. Apollo's triumph was speed and courage, but it left many processes bespoke. Artemis is trying to industrialize the experience, turning heroic improvisation into documented procedure. That shift is less cinematic, yet it is the only way to scale. The heat shield story returns here as a final gate because entry is the unforgiving audit. Artemis I's avcoat cavities forced a redesign of assumptions, not just hardware. The heat shield is a chemical machine designed to char, ablate, and carry heat away through controlled sacrifice. If the material behaves unexpectedly, the margin can vanish in minutes. Re-entry does not negotiate, it simply applies physics. NASA's switch to single-pulse ballistic entry is a trade against unknowns. Shorter heating exposure is chosen to reduce internal overpressure risk, even with higher peak loads. A skip entry can spread heating over time, but it also complicates the thermal profile. A ballistic path is simpler to model, and simplicity can be a form of safety. The capsule will hit the atmosphere hard, then endure a shorter, more intense punishment. The root cause debate does not vanish. It is bounded by evidence. Ground tests, material characterization, and flight data close the uncertainty enough to move forward. Engineers cut samples, image voids, and compare predictions against sensor traces. They also adjust manufacturing and inspection because quality control is part of performance. The goal is not perfect knowledge. It is confidence that unknowns are contained. This is how the program manages residual risk without pretending it is gone. It builds layered safety, then chooses the path that fails more predictably. Redundancy, fault detection, and conservative operations become a philosophy. When a system degrades, the crew must have options that do not require miracles. Deep space rewards designs that degrade gracefully. After Artemis II, NASA's strategy shifts from monuments to logistics. The agency is restructuring around what can be repeated, supplied, and repaired. That is a historical pivot, because the early space age was built on singular feats. In the 1960s, the objective was to arrive first and return alive. In the 2020s, the objective is to stay functional and keep returning. Gateway is deprioritized as a near-term centerpiece because it is not the only way to stage landings. Surface capability becomes the bottleneck, not orbital real estate. An outpost in lunar orbit can be valuable, but it is also another system to power, maintain, and protect. If the surface cannot be supplied reliably, an orbital node does not solve the core problem. The architecture must follow the bottleneck, not the symbolism. The course correction is visible in mission sequencing. Artemis III shifts toward LEO docking demonstrations and suit readiness, because interfaces fail before flags matter. Docking in low Earth orbit allows frequent rehearsal, better tracking, and easier contingency support. Spacesuits are not costumes. They are miniature spacecraft with life support and thermal control. If a suit cannot be serviced, tested, and trusted, a landing is a liability. The first South Polar landing moves to Artemis IV, trading spectacle for systems maturity. The program is choosing fewer heroic firsts and more verified steps. That decision can look like delay, but it is also a form of acceleration. It accelerates learning because it reduces the chance of a catastrophic reset. It treats time as a resource to be spent where it buys down risk. That choice reflects what Artemis II revealed about deep space. The hard part is not reaching the moon. It is operating there without constant improvisation. The moon is close enough to tempt complacency, yet far enough to punish it. A minor failure can become a mission-ending cascade if it consumes crew attention. Artemis II is meant to expose those cascades while the mission is still short. Infrastructure becomes the real mission. Terrain vehicles, cargo handling, power generation, and resource extraction replace symbolic payloads as the center of gravity. A base is not a habitat alone. It is a supply chain with wheels and cables. Regolith is abrasive, thermal cycles are severe, and shadows can be permanently dark. Every piece of equipment must be designed for that environment, not for a brochure. A South Polar campaign needs mobility to reach shadowed regions and sunlit ridges. It needs power systems that survive long nights and dust, and it needs spares. The lighting is stark, with low-angle sun carving long shadows across crater rims. In permanently shadowed regions, temperatures can plunge to cryogenic levels. A vehicle that crosses that boundary must manage traction, thermal shock, and navigation without familiar landmarks. Resource extraction is treated as risk reduction, not science fiction. Water ice can become life support, radiation shielding mass, and propellant if it can be processed reliably. Water can be split into hydrogen and oxygen, but that requires energy and robust hardware. The real challenge is consistency. Mining, heating, capturing vapor, and storing products without losing efficiency. A small failure in a seal or a valve can erase the advantage. Surface logistics also dictates politics. Whoever can move cargo, share power standards, and maintain comlinks will define what cooperation looks like. Shared connectors and voltage standards can make collaboration easy or make it impossible. A common docking adapter can enable rescue or prevent it. In that sense, engineering decisions become diplomatic decisions. Far-side access becomes part of that logistics story. A relay network is not only for astronomy, it is for industrial operations that cannot tolerate silence. A rover hauling cargo cannot pause for hours waiting for Earth to reappear. A drilling operation cannot be left blind during a critical step. Reliable communication turns the far side from a romantic mystery into a workable district. The moon becomes both archive and construction site. It stores the history of impacts, and it offers the nearest place to practice living under that history. The same craters that tell a story also create terrain hazards and thermal traps. The same vacuum that preserves ancient records also complicates every mechanical joint. The moon is a classroom that grades harshly, but it grades honestly. Then the narrative widens again, because the moon is not the end point of the hazard. Mars' transit time and radiation dose remain the next wall. A journey to Mars stretches exposure from days into months, and it multiplies the consequences of small failures. Food, water, and spare parts become heavier burdens. Psychological isolation becomes a variable that cannot be solved by a quick return. Nuclear thermal propulsion enters as a response to cosmological exposure. Concepts like SR1 aim to cut travel time, which cuts dose and reduces consumables. In nuclear thermal propulsion, a reactor heats propellant directly, producing high exhaust velocity without chemical combustion. The promise is not speed for its own sake, but reduced time in the radiation field. Less time in transit also means fewer opportunities for systems to degrade. NTP is not a magic engine, it is a risk management tool. Faster transits reduce time in deep space radiation, and they expand abort options. If something goes wrong, The ability to change trajectory quickly can preserve crew safety. Shorter missions also reduce the mass of food, water, and oxygen that must be carried. The engine becomes part of a broader strategy to keep the mission within manageable bounds. The same logic that shaped the free return trajectory shapes propulsion choices. Architecture is built around graceful failure because the universe does not offer rescue. A free return path is a promise that physics can bring you home even if engines fail. A propulsion system is judged not only by performance, but by how it behaves when it degrades. The design question is always the same. What happens on the worst day? Artemis II is therefore not nostalgia, even when it echoes Apollo. Apollo proved humans could touch the moon, but it did not prove a durable operating system. Apollo's missions were short, intensely supported, and tailored to specific objectives. Artemis is aiming for repeatability, where each mission strengthens the next. That is a different kind of ambition, and it requires different evidence. Artemis II is racing to prove durability. It tests the mundane systems that make exploration scalable, and it turns them into standards and procedures. The crew's sleep logs, exercise sessions, and toilet maintenance become part of a blueprint. They show what it costs to keep a small atmosphere stable for days. They also show where the hidden costs live, in minutes and watts and attention. The biomedical experiments become another blueprint layer. They begin the long work of predicting how radiation and isolation reshape the body over months. The objective is not simply to measure harm, but to map vulnerability windows. When does immune function dip, and when does it recover? Which tissues show early stress signals, and which remain stable? Those answers will shape habitat design and mission timelines. The comm blackouts become a third layer. They teach how to operate when Earth is blocked and how to replace constant contact with planned autonomy. Procedures must be written so they can be executed without immediate clarification. Decision authority must be distributed because waiting can be dangerous. In the silence, the crew learns what it means to be truly away. The docking rehearsals become a fourth layer. They prove the choreography needed for distributed missions, where no single launch carries the whole solution. Docking is alignment, sensing, and controlled force, performed with limited propellant and narrow margins. The interfaces must handle misalignment, thermal distortion, and sensor noise. A successful docking is a quiet triumph of standards, because it means different elements can become one system. All of it answers the central question in a different register. Artemis II is racing because it must turn deep space from an event into a condition. A condition is something you can plan around, train for, and budget for. An event is something you survive once and then mythologize. Artemis is trying to replace myth with method. Earth's magnetic cradle made our species confident, but it also made us forget the baseline. The baseline is vacuum, radiation, and impact history written into stone. The camera can cut from a blue Earth to the grey moon, and the contrast feels like a moral lesson. One world is wrapped in cloud and color, the other is exposed and quiet. The difference is not aesthetic, it is protective infrastructure built by nature. The moon reminds us that violence is normal at planetary timescales. Earth survives partly because it has shields, and partly because it has been lucky. The cratered surface is a reminder that impacts are not hypothetical. The radiation environment is a reminder that particles do not care about intention. In that context, survival is not bravery alone, it is preparation. Humanity's next step is to engineer luck into systems. We build shielding, propulsion, comm relays, and norms that function like a manufactured magnetosphere. That magnetosphere is not only metal and software. It is agreements, interfaces, rescue doctrine, and the habit of measuring reality instead of hoping. The most important sensor may be the one that tells you a problem is small before it becomes large. Artemis II is the first operational proof that this manufactured protection can work beyond Earth. It crosses behind the moon, returns through plasma, and turns survival into repeatable practice. The re-entry blackout. when ionized air swallows radio waves, becomes a ritual reminder of dependence on physics. The parachutes, the splashdown, and the recovery are not an ending. They are a verification. The loop closes, and the blueprint gains another line. The race is not to plant a flag before someone else. The race is to learn how to live in the space between worlds, before the universe reminds us how exposed we are. And when the capsule is recovered, the mission's meaning is not in the scorch marks or the record distance. It is in the blueprint that remains, and in the decision to keep building it. Across these chapters, the story kept widening, from a rocket and a capsule to a new map of risk, where low Earth orbit is still sheltered. Artemis II matters because it tests a repeatable deep space loop: people, procedures, life support, autonomy, and recovery, under radiation, micrometeoroids, distance, and delay. And it matters because the moon is two things at once: the nearest archive of cosmic violence and the nearest construction site for a civilization that plans to last. The urgency is not a countdown to glory. It is a race to harden norms before cislunar space hardens without us, through default standards, supply chains, and competing claims. The accords, docking rules, comm protocols, safety zones, and interoperability aren't paperwork. They are the operating system of a place with no nearby referee. Artemis II is where that operating system meets physics, where a free return trajectory becomes a philosophy of layered safety, and where the crew's training becomes the final redundant system. Even the mission's most anxious subplot, the heat shield, points to the same truth. Because survival is always a chain. A ballistic entry may reduce the chance of avcoat spalling, but only flight data and post-flight inspection can close the root cause debate and turn mitigation into standard. The same is true for the quieter risks: ECLSS motor controllers, batteries, leaks, integration seams. Because cadence is not speed, it is the ability to prevent unknowns from aligning. So what are we really trying to outrun when Artemis II seems to be racing back to the moon again? We're outrunning complacency, because outside Earth's magnetic cradle, the universe isn't scenery, it's a background rate of harm, and the only answer is an architecture that makes exposure survivable. Artemis II doesn't prove we can visit the moon, it proves we can close the loop behind it, across that brief radio silence, and come home on purpose. In that loop, politics becomes logistics, logistics become standards, and standards become the difference between exploration and habitation. If Artemis II succeeds, its real payload won't be names on a drive or relics in a pouch. It will be a new kind of confidence, earned rather than declared. The moon will still look like a destination, but we'll understand it as a test range for the space between worlds, and the first blueprint for living in an indifferent cosmos. Because the universe is not waiting to be conquered, it is waiting to be endured, measured, and negotiated with, burn by burn, rule by rule, until home becomes something we can build. When the mission flies, watch the data as closely as the spectacle, because the future will be written in margins, standards, and what the heat shield tells us on the way back.